From the world's deepest rivers.
It was incredibly deep water. It was deeper than the North Sea, a lot of it.
To its tallest mountains.
You can see the cloud coming in. You can feel the temperature drop.
Railways have set out to conquer them all.
There are 6 different types of structures in place to stop the landslips derailing trains.
What an incredible machine. Absolutely amazing.
Driven by daring engineers for whom no obstacle is too great.
Oh, this is my kind of fun now. I truly love this structure. It's magnificent.
In this episode, tracks and the city. Uniquely urban challenges.
Some of the deepest tunnel in London. Crossrail is Europe's biggest construction infrastructure project.
And the ingenious solutions.
When the train moves, it has to swing.
When the freight gets onto the barges, there's this loud of the metal moving.
That make the impossible possible.
Lisbon without trams will be like Venice with no gondolas.
Despite being able to cover vast distances quickly and efficiently, railways aren't only used for epic cross-continental journeys. For more than 150 years, railways have been serving the world's cities, keeping them functioning, getting us to work, ferrying tourists to attractions, goods to market. They are the arteries that keep many great metropolises alive. But the urban environment poses a very distinct set of problems.
New York City is one of the biggest and busiest in the world. And yet, incredibly, it's cut off from the supply lines that serve the rest of the country.
We're in London, and you're mining in clay, which is a softer material. It does have a tendency to squeeze, and obviously there's a lot of sensitive buildings up above us.
The terrain in Lisbon, it's difficult. It's the city of 7 hills.
And it's one such seemingly impossible city challenge that once faced the 19th century railway engineers of Germany. Imagine you're a growing industrial region that is desperate for a good transport system. But high groundwater levels make tunnelling impossible. And a hilly terrain. And a flood-prone river. Pour cold water on any plans for a traditional rail line. That's exactly the situation engineers were facing in Wuppertal, Germany. By the late 19th century, the booming centre had reached an all-time population peak of 400,000 and quickly needed an efficient mode of transport. But with its packed streets and uneven terrain, all but the most extraordinary railway would be impossible.
You cannot imagine Wuppertal without it. We need this noise. This is just like a melody to us. It's like a music.
The Wuppertaler Schwebebahn, literally Wuppertal's floating train, was opened in 1901 and is still carrying the local population through the seemingly impenetrable cityscape today. Including local guide Gisela Rohleder.
The this railway is certainly one of the most unusual railways. It is in fact an ingenious design. Nobody could imagine to have such a masterwork of techniques here in our tiny town. It looked really futuristic.
This impossible railway is the brainchild of inventor Eugen Langen, who, unable to tunnel or disrupt the city streets, decided to put a monorail on top of the city's river.
It's designed for the city, for this narrow valley with no space. So it was possible to construct it rather all the way along above the river, not requiring any supplementary space.
Langen's design could straddle the river and nearby streets using a steel upturned V design, and so avoiding digging in the waterlogged land or demolishing areas of the city.
It has been constructed in a height of 12 meters with a steel frame having nearly 1,000 legs, something like a caterpillar.
Following the city's river was a brilliant solution, but threw up another challenge. The windy river route meant that a traditional monorail that rigidly straddled the track would not be able to cope with the centrifugal forces at speed. So Langen turned railway engineering on its head, flipping the cars under the line and giving the floating train's passengers a unique swinging ride.
When the train moves around the curves in the track, it has to swing. And it swings up to 15 degrees to the sides, depending which side we go in the curve. Just now, for example, we swing to that side, to the left. Now we go the other way around in the curve, and we swing to the right.
It's like riding a bicycle, but upside down. As you can see, it's quite easy to put it into a slight swing.
That ability to swing is essential to the Schwebebahn's success.
The vehicle needs to swing because you can make tighter turns, and the force on the passengers is very small. The system is unlike any other system in the world.
This unprecedented flowing motion would have been impossible without some inspired engineering on the train itself. Today, project manager Marcus Schawate is overseeing essential works on the Schwebebahn's vital wheels.
We are in the workshop of the Schwebebahn. They're doing some maintenance today. Now we have to maintain here the wheels of the new Schwebebahn, and we have to remove one wheel of this complete set. So these wheels have a maintenance period from about 200,000 kilometers, and then the wheel has to be changed, to be exchanged for a new one.
Positioned above the train, the design of the Schwebebahn's supporting bogie assembly, including its wheels, is unique. To appreciate this, you need a view you can't get from street level.
We are now on the top of the workshop, and we are actually above the track, and you see the bogies of the vehicles. You see gearboxes, the left and the right one, and in the middle the motor. The track is a normal railway track, as you see, and the wheel is quite different because the wheel has two edges. A normal railway wheel is different because it has only one edge, and there are two wheels on a normal railway system.
As the Schwebebahn operates underneath the single rail, this twin-edged wheel design ensures the train remains safely attached at all times. Throughout its history, this impossible railway has been at the heart of Wuppertal. The Kaiser himself travelled on board, along with thousands of commuters. And in the mid-century, one surprising traveller jumped aboard.
In 1950, we had a very particular passenger in the Schwebebahn. And this passenger was a little elephant baby, 3 years old and 650 kilos of weight.
With the circus in town, Baby Toothy's ride seemed a perfect publicity opportunity. But he didn't agree.
It started to panic after a few seconds because it was not at all used to the noise this train made. It smashed all the furniture and smashed as well the side wall of the train so that there was a big hole in the side. And before reaching the next station, the elephant jumped out of the train into the river.
Happily, Toothy survived the fall and was undoubtedly more at home in the muddy waters of the Wupper. Today, around 25 million satisfied passengers ride the Schwebebahn every year. For Marcus, its incredible popularity means it's time to evolve.
Most of the trains are in operation since 1972. Each train covered about 2.5 million kilometers. So it's time for a change.
When the upgrade is complete, the new 31-strong fleet will mean passengers will have no more than a 2-minute wait for their train.
The increasing of this service is because of the number of trains and the new technology. One train can drive closer to the next train.
The charm of the old stock is undeniable. But the future is bright.
So we are now on the new vehicle, and you see it's much brighter and more friendly. The difference to the old vehicle is that the windows are bigger and even the seats are a lot more comfortable. Yes, I've ridden it as a passenger and it's quite beautiful and it's very good.
Old or new, this groundbreaking railway is the making of this city.
Wuppertal without the Schwebebahn would not be Wuppertal. That would be something else. It belongs to Wuppertal since more than 100 years. That's one thing, Wuppertal and the Schwebebahn.
Cities are the setting for some of the world's most ambitious railways. These packed urban environments pushing train engineers to their limits, demanding innovative solutions.
It has been constructed with nearly 1,000 legs, something like a caterpillar.
To seemingly impossible challenges.
We've got one of the largest stations in Crossrail and the smallest space to build it.
To ensure that every day, millions make it to the heart of the metropolis. But for urban railways, passengers aren't the only priority. Cities also rely on trains to keep themselves fully stocked. But when Mother Nature brings them to a grinding halt, keeping the goods coming in can have huge consequences. Congestion and commuter chaos can clog up the streets, leaving the city at a standstill. And if ever there was a city facing these problems, it's New York. With its streets gridlocked for hours on end, the city of dreams is a traffic nightmare. Rail haulage would be the perfect solution to take the pressure off the roads, but trains have a seemingly impossible obstacle to overcome. Water. Everywhere. Dr. Eric Lima is cruising just off Manhattan to discover how the resurgence of a novel nautical solution is helping the city solve one of its longest-standing engineering challenges.
New York City, with a population of over 8.5 million, is one of the biggest and busiest in the world. And so it needs a constant supply of food and goods and materials to keep it running. And yet, incredibly, it's cut off from the supply lines that serve the rest of the country, the freight rail network.
Although passenger trains can access the city, the many rivers surrounding the port of New York have made it largely inaccessible to freight trains. The majority of supplies arriving by trucks, stifling its already congested streets. But thankfully, one impossible railway is providing an alternative.
This is it. This is the New York, New Jersey railcar float.
An ingenious innovation that ferries track-mounted freight trains across a 4.5-mile stretch of the Hudson River.
They're just loading on the last of the rail cars right now, and then those tugboats are going to push it all the way across the waterway into New York City.
With a single rail car capable of carrying 4 lorry loads, the 14-car capacity of the float means it can do the work of 56 lorries in just one 45-minute crossing.
You can hear when the freight gets onto the barges, there's just this loud of the metal moving. Once upon a time, floats like this would have absolutely clogged the waterways. You would have seen them going back and forth because it's the only way to get goods into Manhattan. But now this is the last of its kind that operates on the Hudson and one of the last in the world.
As an historic center of commerce, New York's demand for railway freight stretches back to the 1800s. But faced with this watery archipelago, getting any goods into the city required an overland detour via Albany to the north, adding as much as 36 hours to the journey. It was Brigadier General and former railroad engineer Herman Haupt who first pioneered a more convenient solution. First used during the American Civil War, his simple barge, fitted with railroad tracks, was an inventive idea. But as engineers developed it for the Hudson River, achieving a smooth transition between land and barge posed a sizable problem.
Now this is a tidal river, and that means that the water level goes up and down. And the amount of weight inside of the freight car changes. And that means that the float is at different levels at any given time. And the tracks need to line up. They need to line up on land and the barge so that the freight train could roll seamlessly onto land.
The key to achieving this pinpoint accuracy is a structure known as a transfer bridge.
In really simple terms, this transfer bridge is the portal between land and sea. And I have a little model to show you how it works. And it's quite simple. We have a winch at the very top of the transfer bridge. Now, when the barge comes up, the winch can turn, moving along cables that I have represented here by strings, and it can raise or lower the tracks to suit the needs at the time. So you can match it up perfectly so that it becomes one continuous track.
The extreme engineering needs to cope with enormous forces, as the floating barge, loaded with heavy rail cars, twists and turns in the tidal river. But the system of giant hinges, combined with supersized steel toggle bars, transfer the huge loads through to the bridge's substructure and the earth below.
So this whole thing, it's brilliant.
At its peak, this creative solution for the city's railway transported 6,000 freight cars every day. Today, the railcar float shifts considerably less of New York's goods, but is still a crucial lifeline.
When we think about the city, we don't really think about the freight and the railways that make it possible. But the fundamentals, the things that make it function, make it work, is an old barge that's been quietly carrying tons of freight back and forth daily for years.
And with plans afoot to float 24,000 rail cars across the Hudson every year, this green alternative to the city's congested streets once more appears to be on the up.
And there we go. It just docked. It's completed its journey. It's going to do the same thing tomorrow and the day after. It's an amazing lifeline for New York.
But some cities have to find a completely different solution to overcome their train troubles. When a city grows, so does its population. And so its rail network must do the same. But more trains and more passengers can lead to a fight for space and the potential for chaos. You might think a simple solution would be to go underground, but nothing could be further from the truth. The world beneath the city's streets can sometimes be as busy and as chaotic,
do you mind,
as the one above.
Bit of a squeeze here at the moment. Last beam come down today, is it?
It came down yesterday.
Okay, cool.
As a small army of engineers in London are currently discovering. "150 years since the first beginnings of London's famous underground railway network, an extraordinary new engineering project is nearing completion.
Crossrail is Europe's biggest construction infrastructure project at the moment. About £15 billion. It's 10 new stations through central London, 26 miles of tunnel, some of the deepest tunnel in London, about 40 metres deep in places. There'll be 24 trains an hour, which is about 20% addition to the capacity in this area.
But building it in one of the world's busiest, most densely packed and historically important locations is far from straightforward.
So one of the biggest challenges we've got at Whitechapel is the amount of space to work in. We've got businesses, a school, residents, a sports centre on all four sides of the work. We've got one of the largest stations in Crossrail and the smallest space to build it.
In historic Whitechapel, once the stalking ground of Jack the Ripper, striking a balance between modern engineering and heritage is vital.
The old station is about 140 years old. It's one of the earlier stations. Our role is to take away the old station and form a new station that combines London Underground, Overground and Crossrail together.
As a nod to the past, sections of the old brickwork will be preserved. But removing the remainder of the old station is a painstaking process.
Because of the proximity of the trains at the moment, we've had to do all this work by hand. We can't fit a large machine in to do the demolition. So here it's all been done by hand and taken out in bags during the day.
But for this impossible railway, it's not just the overland works that put the city's heritage at risk. Navigating a railway anywhere in an historic city is a tricky business, even if the engineers go subterranean. All that tunnelling can leave the underground world like Swiss cheese, with potentially calamitous consequences. So how is it possible to build a complex underground system without toppling the national treasures above? Up the road from Whitechapel in London's Finsbury Circus is another huge problem facing project manager Jules Boyd and the engineers of Crossrail every single day.
On the screen here you can see this is a three-dimensional picture of the tunnels related to the surface level up here. This is the building above, and there's the two platform tunnels in the central concourse. And there's a band of London clay which extends just to pretty much the bottom of the tunnels to, what are you, 5 metres into the clay, is it? Something like that? It's about 8 metres into the clay.
The complex computer system monitors when London's priceless architecture is in danger of moving. And today, it's showing that action needs to be taken.
There's a settlement trough emerging under the building.
Urban railways. Feats of engineering that face seemingly impossible challenges as they thread their way through saturated cityscapes. Running these critical lifelines requires inspired solutions.
They're just loading on the last of the rail cars right now, and then those tugboats are going to push it all the way across the waterway into New York City.
Whilst building them calls for cutting-edge technology. And nowhere more so than at London's Crossrail. Connecting the capital east to west, Europe's largest construction project requires 26 miles of tunnels. The sheer scale of the challenge is huge, but at London's Liverpool Street, their engineers have a particularly delicate problem, as they dig directly underneath some of London's finest buildings. With any ground movement potentially catastrophic, project manager Jules Boyd needs a state-of-the-art solution. And it lies 20 metres beneath street level.
This is grouting at it at the east end of the job, underneath some of the works that we're doing, the tunnelling works. Above ground, you've got some of the sensitive buildings called London Wall buildings.
To rebalance any underground areas disturbed by the freshly dug tunnels, the engineers are using an ingenious technique called compensation grouting. Lasers monitor hundreds of points on the surface buildings. If they start to move, even slightly due to the settlement caused by the tunnels, the engineers simply pump a grouting solution into the area to counteract the effect. In the world above the workforce, grand Edwardian architecture is in danger of being undermined.
There's a settlement trough emerging under the building that they're compensating against, and they're about to start the programme for injection. That happens twice a day. How many ports are you going to inject here now? How many different, roughly?
Today?
Yeah.
In the programme? How many boreholes in the programme today?
Cliff Kettle is the principal engineer in charge of the delicate grouting operation.
So down here we've got one of our two main injection plants. We've got one in each half of the gallery. Very viscous grout is being mixed at the surface. That gets pumped down the shaft, comes into a receiving tank here. From the receiving tank, each of these pumps is drawing off, and the pressure is being monitored here and the flow. Here we have our injection control cabin. Down here, the operator is able to see all the pumping characteristics, and he's also got a screen here monitoring what's happening with the buildings on the surface.
There are several sites across London just like this one. Pumping compensating grout into a spider's web of pipes and tunnels stretching out beneath the city streets.
We are standing in this tunnel here, and you'll see each of the holes in the sidewall. You'll just see the end, and this is the distance that they go into the ground underneath the tunnels. The tunnels are these lines below us. This is the Hammersmith and City line. These are the platform tunnels here, and you can see the holes cover pretty much all of the area above the tunnels below. And then above, you can see the road layout. So here are the roads, and these are the buildings that are being protected. This particular building here has a facade that's sitting on the ground surface. The back of the building is built on all of these piles here. It's one of the more technically challenging bits of compensation grouting, where two halves of the building are a different construction and behave differently.
Once this morning's delicate operation is complete, it will continue twice a day, every day, until Cliff, Jules and the team are confident the cityscape above is completely stabilised. Safeguarding history is crucial, but if there's one challenge facing almost all urban railway engineers, it's the geography of the city itself. Most cities inevitably have one thing in common. They were founded.
I name thee Londinium. Lovely jubbly.
And grew long before the invention of the railways. Which means no one chose their locations with trains in mind. Rivers, swamps, hills and mountains.
Hello.
There's no end to the daft places
Goodbye.
that humans have chosen for their homes. Lisbon, founded in 205 BC, may have been brilliant as a port, but it's a nightmare for anyone planning a railway. It's known as the City of Seven Hills, a sprawling mass of windy historic streets and extreme gradients, which provide an exhausting daily climb for its residents. But one ambitious railway engineer thought he had a solution. And the key to its magic lies in a little-known space beneath the city streets, where museum director Susana Fonseca is getting special access.
Now we are in the machine room. Most of the people doesn't know that exists. We are underground.
This unassuming room is the secret behind a truly remarkable innovation that conquered Lisbon's inclines.
Here we have Lavra funicular, the first street funicular in the world. It runs for almost 200 meters in a very, very steep gradient of 25%.
It was the 19th century engineer Raoul Mesnier de Ponsard's inspiration to bring what is commonly used as a mountain railway to the city. Influenced by the trains of the Alps, de Ponsard's funicular replaced donkey power, whisking Lisbon's residents up this extreme gradient in a matter of minutes.
He thought it's the most perfect transport for our hills here in the city. And it worked just fine till today. And they are still reliable and they're still comfortable for making this journey through the hills of Lisbon.
This impossible railway's uncanny ability to climb defies belief. But its solution beneath Lisbon's streets is surprisingly simple. A single cable at the heart of an extraordinary system.
And here is the machine with the cable who made the counterbalance for the funicular to work.
The counterbalance is created as the cable rotates around two parallel tracks on the street above, connecting two trains, one travelling up and one travelling down.
The one who's coming up had no traction to run over the hill, so the one who is going down makes the counterbalance for the one who's coming up.
Originally, this counterbalance was created by adding weight to the descending train. On board, a water-filled tank increased its mass, creating a large force through the cable, pulling the ascending train up the hill. To this day, 3 funicular lines remain, but de Ponsard's legacy doesn't end there. A fleet of historic trams nimbly negotiate the rest of Lisbon's hilly terrain.
People of Lisbon love the trams. It's a symbol of Lisbon. Everyone uses the trams, and we simply love it.
Unlike a conventional railway, the slimline cars are a perfect solution for the capital's tight, windy streets. The city is so passionate about them, modern articulated trams have also been introduced to serve Lisbon's flatter terrain.
We have about 60 trams and 10 million people a year using the tram system, and we are growing.
With this expanding network running almost 20 hours a day, the popularity of the trams is posing new problems for the city's railway engineers. Any maintenance has to be carried out in the dead of night.
Já mandou desligar? Está tudo desligado? It's 1:30 in the morning and we are just beginning. So this job will take at least 2 more hours. In railway, you always have to work at night because that's the time that we have no trams going around. We always have to have our eyes in our main goal, which is never, but never stop the trams.
With the whole tram system now electric, keeping it powered up through Lisbon's ancient streets is a constant challenge for senior engineer Pedro Palma.
Eu acho que eles tinham cortado este fio. Nowadays we have around 67 kilometers of line, and here we are replacing about 50 meters of contact wire. So all this curve is already worn out. Hopefully the new one will last another 5 or 10 years.
And with a new 2.5 kilometre extension to the tram network in construction, Pedro and his team are also part of the railway's future.
It's pretty exciting to be constructing new lines. If we have the right conditions, we can lay down up to 30 meters per week.
The expansion project may be cutting edge, but the team still use traditional welding methods, joining the sections of track with a series of box molds.
The material will be melted inside the box that is put around the rail. And then when we take these pieces out, there will be the new lines.
Once the molten metal is cooled, it's ground down, creating a seamless join.
Meta lá o pé em cima da tangente para eu ver onde é que ela está a bater. We have to be really precise about it. Millimeter precision, that's for sure.
As this latest stretch of line is weaved into the city's streets, the tramways are undoubtedly continuing to shape Lisbon's future.
I'm really thrilled to be part of this expansion because history is being made. For us, railway engineers, to build as we do, it's the most thrilling part of the job, and this is the real deal.
And for the capital's residents, Lisbon simply wouldn't be the same without its impossible railway.
Lisbon without trams will be like Venice with no gondolas.
Cities, home to some of the world's most impossible railways. Feats of engineering taking on huge challenges. From uncompromising street layouts.
It is designed for this narrow valley with no space.
To incredible inclines.
It runs in a very, very steep gradient of 25%.
All to transport billions of us and the goods we need from A to B. Urban railways have a role to play at pretty much every stage of all our lives. And once upon a time, that literally meant from cradle to grave. Engineer Dr. Rhys Morgan is in London to discover how some innovative Victorians used the railways to help solve a rather macabre overcrowding problem. Between 1801 and 1851, the Industrial Revolution saw the city's population more than double to a whopping 2.5 million.
With an increase in the living, there was, of course, an increase in the dying.
And soon London's limited cemeteries were full to overflowing. And with the literal pile-up of dead bodies causing outbreaks of cholera and disease, a solution was desperately needed.
With no city space to spare, the situation appeared impossible. Until two railway moguls came up with an audacious solution. Arguably the strangest train line in British history.
And this is it, the London Necropolis Station. While we think of city commuters as zombies and the living dead, this station actually dealt with the real deal, sending thousands of corpses a year out of the city.
In 1849, Sir Richard Brown and Richard Spry proposed harnessing the power of the railway to relieve London's overcrowded burial grounds. They would purchase a plot of land in the suburbs to create the world's largest cemetery, and then custom build a railway in order to fill it. It would be called the London Necropolis Company.
We're round the back of the station now, and while things have changed over the years, we can get a good sense of what the plan was from this map. The coffins would have been brought in on the hearses through the road just around the back here, and then they would have been brought under a glass-covered driveway where all the pallbearers would have waited. And then the coffins would have been unloaded from the hearses here and then placed on a lift and then lifted a few stories up to track height. And now we're up at track height, and you can see the siding that joins the main railway line to go out to the country. And once the deceased were loaded up onto the train with around 60 other corpses, they would literally begin their journey to the afterlife.
The line took them on a 23-mile ride out of the packed city.
The Necropolis Railway wasn't just reserved for the so-called coffin commuters, but the funeral mourners themselves could travel along with their dearly departed to the cemetery for the burial, and then back on the train that evening, back into the city.
At the literal end of the line for the coffin convoy was the necropolis itself. Brookwood Cemetery, now a 500-acre site with almost 250,000 permanent residents. It was once the largest on the planet.
This is what remains of the platform at the South Station at Brookwood Cemetery. And it was here that the last coffins would be taken off the trains for burial. But because the hearse carriages stacked the bodies 3 high, getting the coffins from the bottom shelf up onto the platform proved to be somewhat difficult. So the engineers came up with a whole range of solutions. First of all, they had a dip in the platform. Now, things have changed here, unfortunately, over the years, but you can just make out here where there's a definite dip where the bricks come down. And that would have helped bring the coffins up from the bottom shelf. They also came up with another ingenious solution, which was to change the shape of the bricks from the sharp edges here to much more rounded, and that would help pull the coffins up onto the platform. You could say it was easing the way of the departed to the afterlife.
Brookwood first opened in November 1854. And given the almost unlimited space in the area, initial plans were for the necropolis to become London's one and only cemetery.
Here at Brookwood, it was hoped that the vast 1,500+ acres of land would be enough to hold the city's dead for an almost indefinite period. And while that wasn't the case, by 1939, it had had over 200,000 burials.
The necropolis ran for almost 100 years, until its closure in 1941, bringing to an end one of the more unusual eras in British railway history.
The London Necropolis Railway provided what was undoubtedly a really successful solution to the city.
For over a century and a half, engineers have overcome huge challenges to build the world's city railways. Striving for innovation, developing inspired solutions.
Right outside of our daily lives, there's a whole secret system bringing all the goods and services that we consume to build that city right there.
Pioneering new discoveries, transforming our modern lives.
Every 3 minutes there is a train. If you lose one, no problem at all. Next one comes immediately.
They have succeeded in creating impossible railways.
There's no doubt that railways have transformed cities. They're altering our modern lives and they're shaping the future. Cities simply wouldn't be the same without them.
Before the invention of the railways, the world was a very much larger place. Scorched deserts, dense jungles, and vast, impenetrable frozen tundra trapped the planet's populations and left travel and trade to only the bravest of adventurers. But trains have opened up these final frontiers, enabling us all to cross even the most deadly of wildernesses, penetrating places once thought impossible to reach. But conquering the world's wildernesses poses uniquely difficult challenges for even the most pioneering of railway engineers.
As you can see here, the landscape is, we are alone here.
We get sometimes very high winds from the southwest, and they can blow up to 200 kilometers an hour.
And you can just see how soft the ground is underfoot. This ground can hardly support my weight.
And it's one such seemingly impossible challenge that faced the intrepid Californian railroaders in the early 1900s. At the turn of the 20th century, the thriving coastal city of San Diego wanted to run a railroad link to the east. But in its path was a desert wilderness, filled with so many lethal obstructions that everyone said it simply couldn't be done. But one man thought otherwise. Deep in the Californian wilderness, engineer Dan Dickrell is riding the rails on board a specially adapted truck. Following a route once dubbed the Impossible Railroad, to discover a truly extraordinary feat of engineering.
Right now we're about 85 miles outside of San Diego, and the terrain outside is as wild as it gets. But where we're headed to this morning is well worth this difficult journey.
In 1906, San Diego entrepreneur John D. Spreckles decided he could defy the odds and build a railroad to transform the city's fortunes. Stretching from the coast to the city of El Centro in southeastern California, it would span an astonishing 238 kilometers across an inhospitable landscape.
Conditions out here are extreme. Temperatures ranging from well over 100 degrees Fahrenheit to well below freezing. There's landslides, earthquakes, floods, the list goes on.
Many thought these massive wilderness challenges would defeat the engineers. And even for Dan and the maintenance crew in a modern high-rail truck, it doesn't take long to discover how the Impossible Railroad earned its reputation.
Working my way ahead of you and
Just right there and then work
just
your
clear,
way back.
clear. All right, I gotcha. How often do you have to do this?
You know, it depends on the wind.
Yeah.
A lot of times we'll come here and it'll be full from there all the way to the other end.
The fact that we're not too far outside of civilization and we're already clearing debris of the tracks is a pretty good indication of how Interesting things are gonna get here quite quickly.
But drifting sand was only the start of the challenges facing the engineers of this desert railroad. As the track rises through the Anza Borrego Desert State Park, this scorched terrain throws up yet more issues.
It's always a big problem here with falling rocks, rock slides, landslides. There's a lot of instability. It's always a challenge to keep the line open.
You throw around the word impossible, but then when you get up into this terrain and see just how steep and rocky and effectively alien it all is, it is truly impossible. And the fact that it's here, though, meant somebody got it done.
And during its 12-year construction, the impossible railroad's biggest hurdle of all was the 18-kilometer-long Carrizo Gorge.
We reached the end of the line for our truck.
A brutal environment that still plays havoc today.
There's one huge obstacle in our way. This landslide, we're gonna have to scramble over, crawl through the tunnel, and emerge on the other side to get where we want to go. Oh, this is my kind of fun now.
In the face of this unforgiving landscape, it seemed the railway's engineers would never succeed. But what Dan is desperate to see is their monumental solution which finally beat nature into submission.
This is the Goat Canyon Trestle. A properly breathtaking engineering marvel. I truly love this structure. Its beauty, its majesty, it's magnificent.
Over 55 meters tall and spanning nearly 200 meters, the Goat Canyon Trestle is widely regarded as the world's largest curved wooden trestle. Incredibly, it was built in little over 100 days, following yet another of the impossible railroad's natural disasters. Before its construction, a train passage through Goat Canyon was along a precarious ledge and through a nearby tunnel. But this route didn't last.
Just ahead we can see Tunnel 15. When a huge landslide broke loose, it partially collapsed the interior of the tunnel, but also dislodged the portal itself, sliding it down the mountain, causing irreparable damage.
The closure of Tunnel 15 was potentially fatal for the project. But with so much money already invested in its success, a bold decision was made. Bridge Goat Canyon to reopen the line. But to build, engineers had the challenge of transporting materials to this remote, craggy location. Anything heavy would be impractical, so they opted for wood. This was a perfect lightweight solution. But with desert temperatures reaching up to 50 degrees Celsius, any crossing train could spark yet another problem: fire.
Now, engineers came up with a very innovative solution. Up there's a water tank, and you can see the pipe that comes down and connects to a series of valves and hoses at various levels underneath the trestle.
Manually operated by a caretaker stationed at the canyon, the gravity-fed sprinkler system would be activated prior to a train crossing the Goat Canyon Trestle.
So here we can see remnants of the old sprinkler system. Water stored in the tank is gravity-fed down through pipes, which you can see extends all the way behind me down the trestle. When the caretaker opens the master valve, the water is distributed through valves and sprinkler heads that dampens the entire structure, preventing a catastrophic fire. It's brilliant.
But the demands of carrying trains over 73 tons across the lengthy wooden trestle posed yet more construction challenges. Nailing the trestle's timbers together simply wasn't an option.
Imagine a train passing overhead. The weight of the train, its heavy load, would cause a significant amount of vibration. If the wooden structure was nailed together, it'd be extremely rigid, ultimately shaking itself apart and removing the nails almost entirely.
Instead, engineers bolted nearly 50 kilometers worth of timber together, forming a semi-rigid structure that allowed any vibrations to pass safely through the trestles into the ground below.
It may seem like a small thing, but the use of bolted fasteners is a big reason why this structure is still standing today.
The Goat Canyon trestle allowed passengers and freight to safely cross the Carrizo Gorge for decades. In an extreme wilderness, this engineering marvel undoubtedly played its part in keeping this ambitious line open. Until, having survived all nature could throw at it, in 2008 this section of the line was finally closed. But now, there are plans to reopen it once more.
Today, hope remains that once again this rail line can carry freight across this unforgiving landscape, giving new life to the impossible railway. Whether those plans succeed or not, the Goat Canyon Trestle remains a monument to human effort, endeavor, and engineering.
They're the railways that tackle the great wildernesses. Trains traversing the world's toughest terrain, posing engineers with seemingly impossible problems, requiring innovative solutions to complete their remarkable journeys. Many wilderness railways cross vast, flat terrain. But when they have to go up, it's a whole new world. Nothing grows, practically nothing can survive. So getting a railway to the top of a mountain is a tall order. Whew. At over 3,000 meters, the steep climbs up the sheer cliffs of the Bernese Highlands in the Swiss Alps are only accessible to mountaineers. You only have to look at this lofty wilderness to appreciate it's the last place you choose to build a railway. However, in the late 19th century, one intrepid train engineer not only took on this unforgiving terrain, he chose to build a railway up through 3 of its most extreme and iconic mountains.
Here we are, standing in front of the famous 3 mountains. The Eiger on the left, the Mönch and the Jungfrau. All 3 of them roughly about 4,000 meters high.
These 3 mighty summits have fascinated poets and artists for hundreds of years. But at the turn of the century, the majestic mountains also started to work their magic on the general public. As interest grew, entrepreneur Adolf Geyer-Zeller was determined to build a railway to bring these mighty mountains to the masses.
People want to see the mountain, and Adolf Geyer-Zeller, he was the man who had the idea to build this railway. He wanted to build the level to the top of the Jungfrau.
His remarkable achievement is the Jungfrau Railway. A railway that climbs 1,400 meters through a vicious wilderness of rock, ice and snow. The end of the line, Europe's highest station. Train controller Christopher Southall knows all too well the challenges of building a railway here.
The weather can change within seconds, really. It can be from a summer 25 degrees here to a winter of minus 25, with extreme weather, high winds, thunderstorms, snowstorms, snow drifting. Today, we're lucky.
Instead of taking the weather on, Geyer-Zeller's audacious solution was to avoid it altogether. He decided to build a train that could climb the inside of a mountain. From the Kleiner Scheidegg base station at 2,000 meters, the initial 2-kilometer route is above ground. But incredibly, Geiersele then chose to dig and blast 7 kilometers of tunnels through the mighty Eiger, Monk and Jungfrau mountains.
This was very difficult and very dangerous to know. There was about 300 employers and 30 people died.
But, as tour guide Roland Fontenive is about to find out, although building a railway inside a mountain avoids the weather, it creates yet another seemingly impossible problem.
Now we go up to Jungfraujoch, top of Europe, by the Jungfrau railways.
Geiersele was operating in a golden age of steam. But coal-powered trains and long underground journeys aren't a good mix.
You cannot go with a steam train 7.3 kilometers in a tunnel, you know. Then in the top everybody will be black, black face. The only option was to go by electric.
But when you're slap bang in the middle of a wilderness, 3.5 kilometers above sea level, finding an electric supply for your train seems an impossible challenge. However, Geiersele turned the wilderness to his advantage, creating another extraordinary solution.
He needed to build hydroelectric power station before they could build the railway.
Geiersele built his very own hydro power plant, 15 kilometers from the railway, providing a dedicated and ready supply of electricity.
The technique, it's more than 100 years old, so we have brand new generators, but it's the same systems like at the start at producing electricity.
Fed from a local river, the power is generated by funneling its water down a whopping 160-meter drop.
This one is from an old generator, and the water from the river is falling like this, and then the wheel is turning, and so with this type we are producing electricity.
Over 4,000 litres of water per second flow through these wheels, feeding energy into the generator above.
As we said, in the upper part is the generator, and here you can see the high voltage cables. So in these cables are 6,000 volts, so we can touch them and it feels pretty warm, so that's the electricity we feel at these cables.
Going uphill, of course, it's just the power of the motors and the electricity getting the train up to the top. But coming down, the motor actually works as a generator, and it's actually generating electricity. 80% is reserved for its braking power, but the last 20% is actually put back up into the power cables. So in theory, you could say 5 trains down, and we send up 1 train for free.
Electric motors drive a rack and pinion system that pulls around 5,000 passengers a day up the steep 35-minute climb.
Now we're coming up to the tunnel.
No matter what the weather.
When we go up in the winter, we didn't have to push the snow away, you know. It's always free, you know. And so you can go up 365 days in the year. I think that time their only choice was to build the tunnel.
During its construction, this hugely ambitious railway's costs doubled. But the industrious Geiersele had forward planned for a shortfall. Partway up his tunnel, he created a station and viewing platform known as IJsmeer, or Sea of Ice. As his workers continued to dig to the top of the mountain, trains would bring paying guests to this midpoint to marvel at IJsmeer's beautiful vistas, raising valuable revenue.
Wow, good. In the beginning, they had some mountain guides. They go hiking with the guests, so you could go outside. I think it's very nice view. You can see in the ice, in the crevasse, you see the crevasse of the glacier.
Today, this is no longer the end of the line for Roland and his fellow passengers. The impossible railway has one more mighty climb to tackle. All this work can create wear and tear, that could see the crucial rack and pinion fail.
Here we have one of our drivers lubricating one of the trains.
To ensure nothing is damaged, engineers have developed a special oiling system.
These two tanks is about 10 litres of oil, and that will be enough for about 1,000 kilometres of this train to go up and down.
Every 50 seconds, the rack and cog are automatically sprayed with an 8-second burst of oil.
It not only lubricates the rack and pinion, the cog, but it also lubricates the wheels, so the track will also have less wear and tear. It is very essential that these trains are lubricated and this oil system works due to possibility of a derailment, which, of course, no train company wants to have.
Brilliant engineering ensures the Jungfrau Railway reaches the end of the line, 3.5 kilometers above sea level. Its passengers confronted with a viewpoint that would have been impossible to reach, but for the toughest mountaineers.
Wow.
Right now we are on 3,571 meters. Yeah, the view is perfect. When people see the view, most people they start to cry. What can I say? Before, only by foot you can come up here. This was something special for people.
It's a view Adolf Geyer-Zeller would never enjoy. He may have died before its completion, but his impossible railway has conquered this great wilderness.
Today, if someone said to build a train through these mountains, you would think they're crazy. But this happened. 105 years ago, they completed it. It happened.
The mountains may pose engineers multiple problems, but the world's railways must cross many diverse landscapes. And one presents an altogether different wilderness challenge: the jungle.
I love the way people just jump in front of the train for a quick photo opportunity.
British travellers Matthew Bell and Philip Holmes are joining the thousands of international tourists each year that journey to the Kanchanaburi region of Thailand.
They don't care about getting on the tracks, do they? They're not shy about it.
All of them drawn to a unique wilderness railway.
That wouldn't happen on the tube. A child standing on the track.
Around 3 trains a day make the 2-hour journey from Kanchanaburi station to Nam Tok and the waterfalls of the Sayok Noi National Park. It's a popular trip.
Come on then. Back we go.
Can we go here?
It's broken.
It's broken. Oh, thanks anyway.
But this is a railway previously thought impossible. Since the 19th century, a wilderness railroad had been considered between Burma and Thailand, but was thought too difficult and dangerous because of the many rivers and hilly, dense jungle. But the middle of the 20th century brought a new world order. In 1942, the armies of Japan captured the British colony of Singapore, enslaving tens of thousands of Allied troops, including an injured 23-year-old gunner, Fergus Ancorn.
The Japanese came into the hospital. They were smashing down the cabinets and taking out the drugs. Then they went out with the walking wounded. And I said to the man lying on the stretcher beside me, "What's going on? What are they doing with them?" He said, "They're taking them onto the front lawn and killing them."
Despite his injuries, Fergus's life was spared. He and around 60,000 other Allied prisoners of war were eventually sent to build what is now a major tourist attraction, the Thai-Burma Railway and the infamous bridge over the River Kwai.
I mean, you've seen the film, right?
Yeah, of course, yeah.
I hear that, you know, that doesn't even come close to the terrible conditions that these people suffered.
By using a workforce of prisoners of war and Asian laborers, the Japanese military had decided they could build this impossible jungle line and use it as a supply route for their armies. It was a decision that would eventually see it dubbed the Death Railway.
The working day, up at dawn, handful of rice to eat, working 18 hours, 30 degrees of sun. Within 2 weeks, we didn't know the days of the week. In the jungle, of course, it was virgin jungle. No one had ever been there. And we had no contact with anybody. And I used to think, I wonder if the war's over. Who won? Are we going to die as slaves?
Wilderness railways. Feats of engineering. Tackling impossible challenges thrown up by the planet's most inhospitable landscapes.
This is the most amazing view in Europe.
But one wilderness railway had to contend with far more than Mother Nature. During the Second World War, the Japanese military brutally used thousands of Asian laborers and prisoners of war to construct a 400-kilometer-long rail line through a dense jungle landscape connecting Thailand and Burma. On the cliffs beside the Kwai Noi River, Gunner Fergus Ancoyne and his fellow POWs would be made to build one of the most extraordinary and iconic engineering features on the line. The Won-Po Viaduct.
Well, the Won-Po Viaduct was an immense affair. It was nearly a mile, I think, and it's round the side of a mountain, about 100 feet up. So we had to blast the mountain away with the dynamite. Very, very dangerous. It was the only job I was on where we had to have elephants to help us.
Today, hordes of tourists, including British travellers Matthew Bell and Philip Holmes, make the precarious journey to experience this seemingly impossible railway.
Fairly vertigo-inducing, actually.
Constructed mainly by hand, the prisoners of war built a teak and concrete trestle that clings to a ledge between the cliffs and the river below. But this was engineering the prisoners were hoping was not built to last.
Apparently, the prisoners of war tried to sabotage the building of the bridge by collecting termites and putting them into the woodwork frame of the original bridge.
That's a bit of a, what do you call a long-term plan?
Yeah, definitely, yeah.
We assembled it, and on every joint we put a handful of termites in every joint, hoping they would eat the bridge when we'd gone. I found out later that they don't like teak. It's hard, they can't do it, so they're still there.
Do you know what? Could you imagine being in that situation then? You had no idea how long the war was going to go on for.
Yeah, well, you probably got to do something to keep your spirits alive.
It has been recorded that 2 shifts of 1,000 men each worked day and night continuously, completing the Won-Po Viaduct in just 17 days.
But I guess, you know, that was the Japanese philosophy on life was, especially around that time, was really different. The Japanese wanted the job done. They wanted to win the war.
Despite mass malnutrition, dysentery and malaria amongst the POWs and the thousands of enslaved Asian workers, the entire railway, with nearly 700 bridges and viaducts, was completed in less than a year, but at an estimated cost of over 100,000 lives.
It's just so sad. It's just so tragic. How could you stand up and be counted? It's like, it's just so anonymous. It's just one of the many number of people who died. I just think it's tragic.
After the war, most of the Wilderness Railway was soon reclaimed by the jungle. What remains is a tribute to the workers like Fergus who survived the so-called Death Railway, and many thousands who didn't.
I don't ever remember saying we made a good job of that. You just did what you were told. I mean, Wampa Viaduct, imagine building that by hand. So we did a good job. It always beats me how the Japanese, who spoke no English, and the English, who spoke no Japanese, built a thing like that viaduct.
Whether crossing jungle, deserts or mountains, the challenges facing a wilderness railway are often apparent. But sometimes hidden problems lie beneath the surface. For rail engineers, nature's obstacles are normally plain to see. They can go through them, under them, or over them. But sometimes the challenges can take you by surprise. The West Highlands of Scotland, a beautiful wilderness enjoyed by millions of visitors every year. But in the late 1800s, this wild terrain filled train engineers with trepidation.
Back in the 1880s, when people were building railways all over Britain, Scotland didn't have that many railways. And the rich fishing grounds of the west coast of Scotland meant that it was absolutely imperative to try and get a railway built down to Glasgow.
Linking the rich pickings of the Atlantic to the rest of Britain would require an audacious railway solution. The West Highland Line. Stretching 198 kilometres from Glasgow to the Highlands Fort William, the Wilderness Line traverses dense forests and extreme mountains, landscape to challenge any rail engineer. But what makes this an impossible railway is perhaps the route's most innocuous scenery, Rannoch Moor.
I never get tired of this moor. I never get tired of the views to the mountains in the background, the small plantations of fir trees.
It may be flat, open terrain, but the 130 square kilometre moor presented a potentially devastating problem for the railway's engineers, as historian Doug Carmichael is about to find out when he follows in their footsteps.
I'm not quite sure we're going to get across this.
Rannoch Moor is essentially one giant bog.
You can just see how soft the ground is underfoot here. On face value, building a railway through here looked like an impossible task. This ground can hardly support my weight, so you can imagine the challenge there was for the engineers to put a railway over it.
With an unstable track, the railway's plans were sinking fast. Engineer Charles Foreman was amongst those who solved this vexing wilderness problem.
The idea was he would use the resources around him. First of all, he took large quantities of this brushwood and laid it on the bogs. Then he took even larger quantities of branches and timber, and then he took turf from all over the moor and laid that on top of the brushwood.
Foreman then topped his natural sandwich with aggregate.
And we get all the aggregate out, and we put it on, and finally I'm going to prove that it works. And it works. The railway did not sink anymore.
Constructed over 5 years with a peak workforce of 5,000, spanning Rannoch Moor's 37-kilometre stretch was perhaps the West Highlands' most hard-won achievement.
I can't imagine what it must have been like all those years ago to build a railway through an environment like this. Quite an incredible achievement.
One area of the boggy moor, however, would need much more than sticks and stones.
They got to here and they found that there was a 1,000-foot wide depression, so they decided they would have to build a viaduct. They had to dig down through yards and yards till they finally hit boulder clay, and they were able to erect these towers. And eventually a 9-span viaduct took shape.
208 metres long, Rannoch Viaduct is the second longest span on the West Highland Line. Beaten only by its most famous crossing, the magical Glenfinnan Viaduct, that has captured the imagination of train enthusiasts and film buffs alike.
The West Highland Line breathed life into remote communities, and more importantly still, tourism came to the West Highlands.
Thanks to inspired solutions, this impossible railway has opened up Scotland's wildest lands. Wilderness, home to some of the most extreme railways on the planet. Built by innovators taking on colossal challenges. From uncharted territory to subsiding soil. Engineers are an ingenious bunch, but there's one thing that can outwit them. As railways continue to reach further and further into the wilds, engineers have learned to adapt to virtually any situation. But one thing's out of their hands: the weather. And in an isolated wilderness, that can be a massive problem.
Help!
Norway, home to a vast frozen wilderness where winters are some of the harshest on the planet. With some areas engulfed by snow for up to 5 months of the year, it's no wonder this is one of Europe's most sparsely populated regions. As project manager Carl Morten Undal is all too aware.
As you can see here, the landscape is, we are alone here. It's about 15 kilometers to the nearest station where people are living, so we are totally alone up here.
This remote Norwegian environment receives huge snowfalls, creating drifts 3 meters deep. Yet, unbelievably, it is home to Northern Europe's highest rail route. The Bergen Railway.
We have a railroad crossing through one of the most beautiful parts of Norway. So I love my work.
During the 1800s, the only way to travel between the major cities of Oslo and Bergen was a week-long voyage by ship. But in 1909, they were connected by this ambitious railway. Travelling east to west, the line first passes through pastureland, but on reaching Geilo, it climbs 1,000 metres in just 100 kilometres, as this railway enters the Hardangervidda mountain range.
Compared to other railways, I think it's extremely challenging. when he did that more than 100 years ago.
But former railway engineer Inga Hjörtas is under no illusion. Keeping the railroad open is an even bigger undertaking.
In a bad winter, we can expect 4.5 meters of snow. You have to be good prepared to stay alive here in the winter.
At 1,250 meters, Sanda, a snow-swept plateau, was once the most notorious section of this wilderness railroad.
This section of the line was the worst when it comes to snow problems. We have to clear the snow 24/7.
Now this section of the railway has been beaten into submission by relentless Mother Nature.
So we had no choice. We had to abandon this track.
Just over 10 kilometers away, Carl and his team must somehow protect the operational line over a 30-kilometer weather-beaten stretch.
On the rest over here, we're going to build around 60-70 meters this way.
Okay.
To catch some of the water coming down from the mountain.
The snow together with the wind will fill up this railroad on just 20-30 minutes on a rough winter day.
Ensuring the impossible railway remains open calls for an inspired solution.
That's not enough time to us to keep the line open with the snowblower. So we need to also have the snow shed protection.
Around 12 kilometers of snow sheds cover the track, keeping up to 7-meter snowdrifts at bay. But many have been in place for over 50 years.
We're now walking in to the old snow sheds built up in a wooden structure with aluminium plates outside. And some of them are actually now in really bad shape. In the summertime we had water problem here, in the wintertime icing. And of course that is not very good for the wooden part here. As we can see, it's rotten.
To keep the railway running, Carl and his team are currently modernizing these aging weather defenses.
Now we're building up a new one with steel and the steel plates also outside. Steel will come up on this concrete wall here. In the winter time, tons of snow will pressure on this wall and we need to secure it safely. Without snow shed protection in this area, it will be a very big challenge for us to keep the railway open.
But even snow sheds couldn't save the section of the now desolate Sanda Plateau. Avoiding the weather here calls for a monumental construction project. An audacious £46 million 10-kilometre tunnel cut directly through a solid granite mountain.
It was opened in 1993 after 3 years of work. And it has made the line much more reliable, and it has reduced snow clearing costs with about 50%. So in around 13 years, this tunnel paid itself.
This engineering success story is just another chapter in the extraordinary history of a truly pioneering cross-country railway.
The Oslo-Bergen line was really a revolution. The line has been very important for more than 100 years.
This line is a lifeline for support the western part of Norway. I would say this is one of the most incredible railways in the world, Bergen Line.
Since the 1800s, wilderness railways have forged seemingly impossible paths through the world's most unforgiving landscapes. Through stunning achievements,
Almost from the very start of this project, people were calling it the Impossible Railroad.
This is an incredible wilderness railway. I take my cap off to the engineers who built it.
And groundbreaking innovations.
They're not ordinary trains at all. Basically, these trains were built for that terrain, a 25% gradient.
Engineers continue to defy the odds, creating impossible railways.
It doesn't matter about the weather when you get here. The train journey up is just the most amazing. One of the top 10 in the whole world for sure.
Many of the planet's greatest railways have inspired great engineering in order to conquer its harshest terrain. But whether carved through vast mountain ranges or cut through impenetrable jungle, arguably any railway's most impressive feat is bridging nature's great divides. From deep river gorges to wide open seas, our railways cross seemingly impossible chasms, connecting both communities and countries. But each of these crossings create engineering challenges that could stop a railway in its tracks.
This is the Mohaka River, and when you look up, you get a really good sense of the huge challenge that the engineers face.
This stretch of water is quite long. We have 16 kilometers from Denmark to Sweden.
You can see it's a very huge valley, and the valley sides are very steep.
It was one such problem facing railway engineers in the US over half a century ago. If you're an island city separated from the mainland, bridging waterways can allow rail supplies to flow, but can leave your vital rivers well and truly blocked. Keeping everyone happy in the city can be an all but impossible bridging challenge. But one railroad in 1950s America proves otherwise. Staten Island in southwestern New York. Sandwiched between mainland New Jersey and Brooklyn, it's a critical gateway into this busy metropolis. One which trains must access. Today, alongside tons of cargo, Professor Eric Lima is experiencing an unrivaled view of the railway.
Oh man, we're on the front of a diesel train right now. The power on this thing is amazing. This freight service is huge for New York.
But getting locomotives into Staten Island means overcoming a tricky geographical problem.
It's the artery that brings all of the goods and services that we use on a daily basis, and we don't think about it when we're in the city, but New York City is completely surrounded by water. So for trains, this is easier said than done.
The stretch of water separating Staten Island from New Jersey, known as the Arthur Kill, may only measure around 170 meters across. But it's packed with boats.
This is an extremely busy waterway. There are thousands of boats that go through. And if you're gonna have a railway across, you're gonna have to have clearance for those boats to go under.
For a pedestrian or a car bridge, getting this clearance is no problem, as rubber tires and grippy soles can cope with an incline. Whereas steel-wheeled trains faced with a quick ascent get themselves into a spin. However, in 1959, the Baltimore and Ohio Railroad got round this problem with a monumental solution.
Wow, this is amazing. It's the world's largest lift bridge, the Arthur Kill.
But it's this bridge's extraordinary actions, rather than its colossal scale, that makes the Arthur Kill Bridge a standout structure.
I mean, that's an engineering marvel.
With a lift span of 170 meters, the Arthur Kill is the longest single-span vertical lift bridge in the world. When lowered for trains, it clears the water by 9 meters, but when raised, the span towers 41 meters high, leaving clearance for even the biggest ships.
Over here at the AK Bridge, we have the bridge drop scheduled for 9:45 a.m. Do you see any problems with that as far as vessel traffic goes?
But for Supervisor of Structures Ryan J. Wagner, it's not all plain sailing. To minimize disruption, the bridge can only be lowered 3 times a day, for just half an hour.
Okay, yeah, I see there. She's coming northbound, right? I'll call when I know she's clear, all right? Okay, Roger, will do. For our bridge drops here, we have to coordinate with the Coast Guard based on the tremendous amount of vessel traffic coming through the Arthur Kill Channel. We have about a half an hour time frame to get the train over and then to have the bridge back in the fully open position.
Lowering and raising a 2,000-ton lift span in such a short window requires supersized engineering. The bridge is fitted with a powerful system of counterweights and cables, driven by motors installed at the top of each tower.
Security, security, security, AK Railroad Bridge coming to a close. Security, security, security, AK Railroad Bridge coming to a close.
With all shipping being kept at bay, Ryan is putting this cutting-edge technology into action.
I've enabled the controls. That's enabled power to go to both drive motors. Once the drive motors are fully energized, they give the command for the bridge to go into the span seated position, and then the bridge starts coming down.
All right, here we go. It's starting.
The concrete-filled steel boxes used as counterweights each weigh a whopping 1,000 tons.
You can see the counterweights moving up right now in the perfect balance to the bridge that's coming down. You really want the bridge to come down exactly level. Both the motors have to work simultaneously, and so that there's no skew, so that the trains can go across, and then we can go across.
After just 2.5 minutes, the span enters its final leveling, a critical phase demanding millimeter precision.
So right now you have the bridge going through its skew correction system. We have a variety of sensors that are basically detecting all kinds of positions of gearing, physical track structure like the rails.
If the tracks don't line up, the trains will miss their crucial slot.
If all those checks are not correct, the dispatcher will not be able to allow a train to pass over the bridge. That causes a variety of issues. Train delays, it impacts vessel traffic because now we have the bridge seated and it cuts into our half-an-hour time frame.
With the bridge successfully locked, now the goods trains and Eric can carry on their journey.
All right, we saw it come down, and now we get the pleasure of actually going across it. What a piece of engineering. I'm looking at it now. I see the giant counterweights above. We're on it seamlessly. You can hear the banging and the clashing, and I see the water underneath. What a brilliant bridge. It's really hard to imagine that this is actually 100 feet higher in the air on a normal basis.
The 170-meter shortcut between New Jersey and Staten Island takes a matter of seconds. The race is now on to get the waterway moving.
Roger. So right now we're starting the process for the bridge opening. You have the warning indication to notify anybody that's on the span that the bridge is going to be opening.
Ryan and his team now have less than 3 minutes to open this impossible bridge.
See the counterweight coming down right here, right now. So at this point now, the span and the counterweight are approximately the same elevation.
Over 50 years after it first came into operation, the Arthur Kill Bridge still manages to return to its open position bang on schedule.
Every day, there's always something new to be learned. There's always something that can be improved upon in terms of its operation to make it more efficient. Yeah, it's certainly something that I enjoy working with.
Every day, the brilliant mechanics of this towering bridge allow tons of freight to be carried in and out of Staten Island.
Without it, there would be no crossing. But with this bridge, the train just went right across. It seems so simple, and yet it's an engineering marvel, and it's really, really gratifying to see it work.
Railway crossings. Seemingly impossible structures spanning nature's vast voids, creating huge engineering challenges, demanding inspired solutions to keep our trains running.
It's really exciting. What a brilliant bridge.
Building bridges throws up many problems, and none more so than height. When creating super tall crossings, the solution may appear to be out of reach. Supersizing can work, if your environment allows it. Tackling it from a different angle may be the answer, but can end in calamity. Nestled in the east coast of New Zealand's North Island lies the Mahaka River Gorge. Its extreme landscape perfect for outdoor pursuits. But you would think its towering ravines and fast-flowing river would put the brakes on any railway. However, one bridge builder proved otherwise.
Hey, buddy.
How's it going?
Good.
Cool. Chuck your life jacket on there, like a backpack. Make sure you get all 4 buckles up, including the one right down the bottom there.
For Heritage Advisor Karen Astwood, there's only one way to appreciate how engineers traversed this impossible chasm.
So this is the Mohaka River, and when you look up, you get a really good sense of the huge challenge that the engineers had here. To get the train across this massive gorge, they had to put up a structure which is 350 feet tall, making it the highest in Australasia and the 5th tallest in the world at the time it was constructed. This would have to be a bridge of epic proportions. And here it is.
This is the Mohaka Viaduct.
That is a truly impressive structure. What a stunning piece of engineering. I'm actually a little bit speechless. It's awesome. It's really great. I love that structure.
Spanning almost 300 meters and 95 meters high, the Mohaka Viaduct has conquered nature.
Not only is the Mohaka Viaduct a thing of beauty, the engineering that made it possible is just as impressive.
Completed in 1937, this was a bridge born from an isolated community's critical need. On New Zealand's North Island, the town of Wairau sits on the northern shore of Hawke's Bay, perched on the mouth of a major river. A wild landscape that 80 years ago threw up many problems.
Wairau could be often cut off from the rest of the world for weeks at a time because the basic dirt roads became impassable in bad weather, and also there's a treacherous sandbar out there in the river mouth, making it difficult for even the smallest vessels to access the town.
A rail connection to the city of Napier, 80 kilometres to the south, and Gisborne to the northeast would offer Wairau a crucial lifeline.
But construction of this vital link was complicated by a series of shattering setbacks, and the immense engineering challenges posed by the North Island's rugged terrain.
And none would be greater than the deep ravines surrounding the Mahaka River. But engineer John Cull believed he could beat the odds with his design for a prefabricated, supersized steel structure. Work started in 1930. With concrete foundations in place, a death-defying workforce nimbly set about its construction high above the valley floor. But the real engineering challenge was getting 1,900 tons of steel to these dizzying, windswept heights.
If you can imagine these two ladders are towers either side of the gorge, then a cableway was strung across the gorge like this. Suspended from the cableway, represented here by these carabiners, was a hook, which moved independently along like this. What this meant is that once you had attached a steel component to the crane hook, like so, it could be moved out into the gorge. It could then be manoeuvred into place and affixed really quickly.
The engineers took this brilliant solution one step further, slinging two cables across the ravine, each one working independently, allowing super heavy steel components to be twisted and swung, positioning them with pinpoint accuracy.
And because the steel components were prefabricated and then brought to site, the viaduct could be assembled like a giant Meccano set, and progress was really, really quick.
Incredibly, Cull's rail bridge was completed ahead of schedule and for half the estimated costs. The Mahaka Viaduct was the final link in the line to Waira, allowing goods and residents in and out of the once isolated region.
Today, Wairau is totally transformed. Thanks to one of the world's tallest railway bridges, this once largely inaccessible town has been given a whole new lease of life.
Creating super high spans is a huge achievement, but when it comes to crossing chasms, railway engineers often face an equally taxing problem. Whether traversing channels or seascapes, trains often have to negotiate wide crossings, presenting their structures with a whole host of problems. That can leave engineers all at sea. And it was one such problem affecting Scotland's capital, Edinburgh, during the 19th century. For this booming city, open countryside to the south and west allowed easy access for trade. But to the north lay the Firth of Forth, a vast estuary renowned for its harsh weather and fast-flowing waters. For a railway to overcome this would take a crossing like no other. The Forth Bridge. The largest steel structure the world had ever seen.
Groundbreaking design. Victorian engineers at their best.
Spanning 2.5 kilometres, 53,000 tonnes of steel and 6.5 million rivets ensure this feat of engineering stands strong against the brutal battering of the North Sea.
The engineering that was involved was the very best of its day. The forefront of engineering, the very best of materials, and we've ended up with a magnificent bridge.
It's the brainchild of engineers Benjamin Baker and John Fowler, who tackled the improbable challenge of a 2,500 metre long bridge with a game-changing design. Their solution, based on balance, was to cantilever the bridge. 3 giant diamond-like structures act as centre points for cantilevered arms. A concept best appreciated from an unrivaled view above.
Where we are just now is on the tower, one tower of the bridge. And from each tower, there are 2 cantilevers, effectively like one arm poking out in either direction, stretching out. And these 2 arms are what's called a balance cantilever. So each balances the other one off.
But it wasn't just the scale of the Firth of Forth that threw up problems. In 1879, its predecessor, the Tay Bridge, succumbed to a major storm. Its collapse tragically killing 75 on board a crossing train.
Fowler and Baker learned a lot from the Tay Bridge disaster, and they had to come up with something that was robust and strong.
To withstand the fierce weather and fast-flowing waters called for rock-solid foundations. But in the deep estuary, this was far from easy.
So if you can imagine the space between the water to the deck level, you've got that same depth of water below there. So it's incredibly deep water. It was deeper than the North Sea, a lot of it.
Building 12 mammoth cylindrical concrete foundations here would be far from straightforward.
What the general public see is actually very top end. If you think of an iceberg, there's a huge amount of work below this actual masonry here. This is the top of a foundation that goes down 30 feet into the actual bed itself, and that's where the caisson was used to actually create the foundation.
The caissons were gigantic twin-walled cylinders floated out and sunk in the estuary. Once pumped out, 20 to 30 men would then excavate the seabed, creating the foundations.
Mustn't underestimate just how arduous and how hard a piece of work that was. Nothing more difficult than digging foundations on the Forth Bridge.
With the underwater works complete, Baker and Fowler constructed enormous piers to take the weight of 2,000-ton trains and over 50,000 tons of steel.
These piers take an enormous load. All the load of the bridge has to come down onto each of these 4 points on each of the 3 towers. The most important part of the whole bridge.
As with everything on this impressive bridge, the solution was supersized.
This is a very special place on the bridge. There's basically very few people have actually been allowed to stand here. Each one of those blocks of stone is a ton. So multiply that by several thousand. That's the scale of one of these foundations, of which we have 12 right through the bridge. Fowler and Baker were at the very forefront of engineering ingenuity. To even imagine a bridge such as this was in many ways risky. Has the risk paid off? No question at all, absolutely.
Extreme crossings, connecting the world's railways in nature's most demanding locations.
Wow, this is amazing!
And one such bridge faced more problems than most. Scotland's Firth of Forth. Home to the staggering 2.5-kilometre long Forth Bridge. Designated a World Heritage Site, this game-changing cantilevered structure is engineering on an epic scale.
If you turned Eiffel Tower on its end, Eiffel Tower would fit into one diamond. That basically is one Eiffel Tower. So have we got 6 Eiffel Towers? I think we have.
Completed in 1890, Its jaw-dropping size is down to a pioneering use of steel, which, unlike its iron-built contemporaries, is super strong, resulting in what was once the world's largest bridge.
Guys, what we're going to be doing this morning is we're taking the safety net out.
Today, however, the 53,000 tons of steel creates an ongoing battle for consultant coatings inspector John MacDonald.
Biggest problem is dropped objects. Can't happen, okay? Everybody happy with that?
Yeah.
Right, great.
Salt water and 140km/h winds relentlessly take their toll.
We need to put a scaffold in to give access to a steel worker to come in to do some cutting for us, to do some welding.
With 200 trains a day passing above, it's crucial this crack engineering team maintain the bridge.
All good.
In perhaps the nation's most precarious workplace.
The net is at the moment tied firmly to the bridge and we're just untying it so we can start to deploy it. It's kind of a curtain system that opens it up. So should we unfortunately drop anything, it will land inside the net. Yeah, good. Good, yeah. Let's have a go. Got a good spot.
Goodbye.
Try and push it out of that push. We're good on this side.
Although 95% of the bridge's steel still exists, the race is on to remove any unsound metal.
In this part of the bridge alone, I think we have scheduled 190 repairs. They're all small scale, but put together, that's quite a lot of work. The repair itself might take 2 hours, but the logistics of getting to the repair, we could be looking at 4 or 5 men working for a week.
And today, like practically every other day, action needs to be taken.
We have 2 pieces of steel make up this component. This one is in very good condition, except for a bottom corner here, we have just a great deal of corrosion. So we're reaching a point where if we leave it very much longer, this part of the member will actually become detached from the bridge. It will fail. We're going to do the repair. This is a very small repair, but eventually you would start to affect the integrity of the bridge if we didn't do these repairs on a regular basis. And it'll be replaced with a new insert welded in place.
But perhaps this bridge's biggest challenge is seen through its iconic colour.
How many coats is this, Peter?
Second coat.
On this and that one?
Yes.
Okay.
John and his team must keep 230,000 square metres of protective red oxide paint up to scratch.
Squads of men go to a select area, chip away, paint, move on to another area, chip away, paint, because the size of this thing, they were constantly playing catch-up.
But now a new solution, developed from the North Sea oil rigs, is brushing away this problem.
On a microscopic scale, it has flakes of glass suspended in the paint. When it's applied, as it cures, these tiny bits of glass settle down flat onto each other, a bit like the scales of a snake, and make more or less a glass cover over the steel, impermeable.
This cutting-edge paint will last 25 years, safeguarding the future of this magnificent railway crossing.
This bridge is in better condition than it has been for the past 75 years, possibly in the best condition it's been in since it was built. Sometimes you just stand back and look at the structure and think to yourself, it's a privilege to be here.
The pyramids were wonderful. This bridge is wonderful. It's up there. I came along here for 6 months and stayed for 23 years. I just love it to bits.
For any railway bridge to remain standing, keeping it in tip-top condition is crucial. But the key to any super strong structure is getting its design right in the first place. take the strain of a train, a railway crossing needs support. But not any old support. For bridges, the right geometry is key. And in Germany, over 150 years ago, one rift in the landscape would push bridge design to its limits. At 500 meters wide and 70 meters high, the Gulch Valley in the state of Saxony is a spectacular sight. But as Professor Lutz Nietner is finding out, in the 19th century, it was also a seemingly impossible hurdle for the railways.
In the beginning of the 1800s, the engineers had a task to build a new railway connection between the towns Leipzig and Hof, and their problem was to cross this valley. It's a very huge valley, and the valley sides are very steep. So the trains of the time had the problem that they hadn't enough friction on the rails.
Heavy steam engines of the day struggled on any significant slopes. So building a line down into the valley was out of the question. A bridge was the only answer.
This bridge has to be very enormous span and has a very enormous load capacity to hold all the trains rolling on them.
The bridge would be unlike any other in the world. And even today, for those that cross it,
After the corner, we cross the bridge.
this railway's mind-blowing solution still takes the breath away.
It's a very nice picture, driving over the bridge. I'm lucky. She's the greatest bridge in Europe.
The Gulch Viaduct is the largest brick-built bridge in the world.
So the simple solution is always the best. And that's what you can see here, the Gulchtal Viaduct.
Stretching 574 meters and towering 78 meters high. When opened in 1851, it was the tallest railway bridge on the planet.
For me, it is a masterpiece of engineering. I love it.
The bridge's extraordinary dimensions are down to one man, engineer and mathematical genius Johann Andreas Schubert. He knew that spanning such massive distances whilst taking the strain of a train could only be achieved by one simple shape.
Schubert was the first engineer who proved the stability of his constructions in a mathematical way on the paper. He relied on the mathematical principle of an arch shape.
For centuries, the strength of this classic shape has defied belief, allowing buildings and even the most surprising everyday items to withstand incredible loads.
On the first sight, an egg seems to be a very fragile thing. If you tap it on a hard surface, it can be easily broken. If you can see here, the egg is shaped like an arch, and we want to try to stack some bricks on them. Now this is the crucial point. At this moment, the load from the brick concentrates on these 4 eggshells. Let's see what happens if we stack another one on it. So we have just doubled the forces in the shells of the egg. Let's see if there is a 3rd brick. The total load of all these bricks is concentrated on the 4 points of the eggshells. The load is distributed through the compressive strength of the shape of the egg onto the table. That's what we have in the bridge behind me. The arch shape is an essential element of civil engineering.
With the load-bearing capacity of arches proven time and again, could they withstand lateral pressure like that of a train? Schubert created a mathematical formula proving they could do just that.
Schubert's formula has a very great effect on bridge construction in that time, because he was able to prove in a mathematical way that such a simple design has a very high load capacity to carry rolling loads on top and to transform these tensions into compressive ones.
Safely carrying trains across the enormous Gulch Valley would take 81 arches built over 4 stories. An elaborate design, which also had to be built on a budget. Sourcing materials locally, Schubert's solution was to build with bricks.
It was the cheapest and easiest way to have a material because of the local clay pits here. It was quite unusual in that time to use bridge for such enormous constructions, because bricks don't have so much compressive strength. So what you need to do is to combine a lot of them to have a lot of area to put forces through.
It would take over 26 million bricks to span the chasm.
A normal worker would have to do 1,600 bricks a day. And this is a very challenging work.
After 6 years, nearly 2,000 workers finally completed this record-breaking structure in 1851.
Looking from this point, I feel very small compared to this massive bridge.
Today, this chasm crossing still stands up to modern engineering, as intercity trains travelling at over 100 kilometres an hour glide over its historic arches.
It is incredible what has been built 165 years ago. This bridge is an amazing piece of engineering.
Many of the world's greatest crossings have been built for the railways, straddling deep gorges, traversing wide open valleys, keeping our journeys on track.
It is a masterpiece of engineering, and I love it.
But sometimes the obstacles can appear beyond the bounds of possibility. This is the Øresund Strait, an immense waterway forming a natural boundary between Denmark and Sweden. With its notoriously busy shipping channel and close proximity to an airport, it's the last place you'd expect to find a railway crossing. For centuries, it was only possible to cross by boat, and even that isn't easy.
We have 16 kilometers from Denmark to Sweden, and during wintertime, for example, you can have ice in this area. We've had up to 40 centimeters of ice, so you can actually not go by boat many days during wintertime. So there were days where we couldn't come from Denmark to Sweden.
For many, building a transport link to connect Sweden's Malmö and Denmark's capital, Copenhagen, was just a dream.
It's quite difficult to build because we need to have the road traffic and the train traffic in the same structure. So it's very, very big structures we talk about.
The solution would have to be like no other. The Øresund Bridge, the longest cable-stayed rail and road bridge in the world. At 8 kilometers long, engineering on this scale required around 142,000 tons of steel.
It was seen as one of the biggest engineering challenges. Engineers came from all over the world in order to see what we had done here.
Despite its size, for civil engineer Niels Lukeberg, the biggest challenge was thrown up by its location, one of the world's busiest shipping lanes.
Due to the very large number of vessels passing through Øresund, we had to leave a stretch of water open for the traffic in order to avoid congestion.
The answer? A colossal centerpiece off the Swedish shoreline. Construction begins in 1995. Huge sections of the bridge are prefabricated and towed into position. Out of the water grows a pair of approximately 200-meter-high pylons, built to support a half-kilometer-long span for ships to pass beneath.
This bridge is designed for navigation purposes with a clearance height of 55 meters, so even very large ships can pass through.
However, in this 16-kilometer-wide strait, a shipping passage is also needed off the Danish coast. But here, a bridge is out of the question.
There is a special problem because we have the Copenhagen airport, which is quite a big airport, so close to the strait here. We could not build a bridge on the Danish side simply because the high pylons, they would conflict with the runways.
Remarkably, instead of going over, they now decide to go under. This is a bridge that morphs into a tunnel.
We are just on top of the entrance to the tunnel. The tunnel itself is constructed of prefabricated tunnel elements, which are 40 meter wide and 60 to 80 meter long, floated to this location and submerged into the trench. We ended up with a 4-kilometer long tunnel. That had never been done in that scale before. It is the biggest immersed tunnel ever constructed in the world.
Digging the trench for this record-breaking tunnel produces 7.5 million cubic meters of material from the seabed, used to create the Øresund's third astonishing landmark. A 4-kilometer man-made island in the middle of the Baltic Sea.
This was an open water area in the middle of Øresund, and now it's an island linking the tunnel with the high bridge and thereby forming a part of the link to Sweden.
Opened in 2000, this hybrid link has transformed the region, connecting two countries together.
Before it took more than 1 hour just to pass the water, and now it can be done in 7-8 minutes.
Whilst 20,000 cars pass over the bridge every single day, 60% of people crossing take the train. And the shipping lanes continue uninterrupted.
Is it a dream job? Yes, of course it is. I've been on many projects in my lifetime, but this one will stand out as one of the biggest challenges we had and one of the biggest successes we've had for this type of lens.
For over 150 years, bridges have opened up the world to trains, allowing them to cross seemingly impossible divides.
We think about technology, but it's the hardcore bridges that are the things that really make everything possible.
Thanks to inspired solutions.
That's a wonderful piece of engineering. It's a wonderful piece of architecture. There's no reason why this shouldn't be here for another 100 years plus.
Engineers continue to create their impossible railways.
Bridges are among the most important components of railways all around the world, helping trains reach their destinations by overcoming formidable obstacles that stand in their way.
Since the first railways were rolled out, they have explored new frontiers, conquering nature at its most extreme. No matter what lies in their path, inspired engineers endeavour to find a way through. But there's one geographical challenge that stands above the rest. Mountains. Overcoming the planet's highest peaks requires phenomenal railways. But they face a unique set of problems.
Behind me we've got the Lithgow Valley, and in front of me we've got Sydney. And these mountains basically act as a great divide between city and country.
The geological conditions are really difficult here. The danger that rocks are falling down is high.
This area has very deep fjords and very steep mountainsides, so it's really difficult to build anything here.
Travelling through mountains is a huge challenge for both track and train. History's locomotives have achieved great things. From the pioneering days of steam to the efficiency of electric and the mighty modern-day diesels. All have made their own mark, but have one thing in common. They struggle on anything steep. It takes a very special railway to climb mountains. On the wild west coast of Britain lies the spectacular Snowdonia National Park, for centuries a mecca for climbers. At the centre of it all, the summit everyone wants to ascend. Mount Snowdon. But at over 1,000 metres tall, these stunning views were once reserved only for the brave. At the end of the 19th century, however, one man decided he wasn't content with merely hiking to the top. He wanted to conquer the tallest mountain in Wales by train. Snowdon Mountain Railway has been clawing its way through the clouds for more than 120 years.
Engineer 1, Snowdon 1.
Mike, pass the message, mate.
Yeah, just to confirm, I believe number 5 is going out first.
This morning, they're preparing the historic rolling stock for another remarkable attempt on the summit. It's been an all-night process.
It's always a busy time prepping for the day. So steam locomotives, they've been in steam overnight with a fireman on watch.
Some of the locomotives are over 120 years old, and they're facing a seemingly impossible near 8-kilometre climb.
The terrain is difficult. The steepest gradient on the mountain is 1 in 5.5. For every 5.5 metres, the track rises a metre. So it's quite steep.
This daring adventure is the brainchild of one man. Railway tycoon Richard Moon had a vision of bringing the mountain to the masses. Today, fireman Elizabeth Partridge, driver Robert Henry Jones, and general manager Alan Kendall are all following in Moon's footsteps as they and a carriage full of adventurous tourists attempt the journey to the top.
Okay, ladies and gentlemen, can I have tickets, please?
But it's far from certain they'll make it all the way.
We are on wind warnings today. If wind speed increases on the mountain, we may be forced to stop at Rocky Valley, okay?
There'd always been an interest in getting to the top of the mountain for 300 years, really, and prior to the railway, people walked and hiked and climbed and also went up by donkey and horse.
Moon's proposed route started from the base of the mountain, passing a sheltered rocky outcrop to traverse a 1-kilometre long exposed ridge, before ascending the last 200 metres to the summit. But no traditional railway could ever provide enough traction to scale the steep incline. A fact clear to current senior engineering manager Mike Roberts-Shaw, down below in the yard.
Well, in a normal railway, all the traction and braking forces is carried out by the steel wheel on the steel rail. In our case, because the gradients are so steep, you get no adhesion between the steel wheel and the steel rail, and the locomotive would just sit and spin or slide backwards.
Mobile 5 to Snowdon 1, stopped at Hebron.
The consequences of slipping back down such a gradient are unthinkable. But there was a possible solution, one that had been perfected by a Swiss engineer just a few years before.
The absolute only option to go to the summit was a rack and pinion railway.
Unlike a traditional train where the power is transferred down an axle to the wheels, Moon's Snowdon locomotives have a cog on the axle, which connects with a toothed rack running between the rails, meaning getting enough grip is no longer a problem.
Well, this is a rack and pinion railway. This part is the rack, and these are the pinions. And on the main track, there's a pair of racks, and on the locomotive, there's 2 driven axles, each with a pair of pinions. So the pinion, there's always 2 teeth fully engaged in the rack.
It was a brilliantly simple solution to a once impossible problem. But whilst the system can cope with the gradient, the unforgiving mountain climate is another matter.
The weather on Snowdon is always a challenge all the year round, and particularly in the winter. We are in July. You can see the cloud coming in. You can feel the temperature drop.
Mobile 5 to Snowdon 1, do we have an idea on the current wind readings?
Snowdon 1, Mobile 5, yeah, the last wind reading at 45 was 45.1.
If the weather deteriorates today, the train will be forced to terminate some distance below the legendary summit. Cloud and mist have shrouded the peak just as they did on the railway's opening on the 6th of April, 1896. After successfully reaching the summit, locomotive number 1 started its descent, but having lost control, jumped off the rack. The crew leapt clear, but the runaway engine derailed and fell over the side of the mountain. Some way below, a climbing group told of looking up, only to see a steam locomotive falling out of the cloud. After an inquiry, additional gripper rails fixed around the track's rack would lock the trains firmly in place. Today, it's an anxious wait for crew and passengers, while control decides if the weather is too severe to continue to the peak.
Paul, you may proceed up to the summit on 09, mate.
Mobile 5 to Snowdon 1, proceeding up to the summit on 09.
It's good news. But first, the train must navigate the steepest part of the track.
The upper mountain is a serious gradient, 1 in 5. We're currently travelling on an original locomotive from 1896. You can look out of the window and you can see the gradient behind you. You can appreciate just how hard that boiler has to work and the pressures that it has to create.
The steep gradient means an ordinary boiler would be unable to cope. A traditional steam engine boiler consists of a cylinder filled with water surrounding a series of pipes. All very good for travelling on a flat line. But if you're trying to climb a mountain, as the train tilts, the changing water level exposes the pipes, with potentially calamitous consequences. So how can the danger be averted?
So this is one of our locomotives that we're doing some work on. And this part here is the boiler. And as you can see, it's inclined forward at an angle. And that's so that when the locomotive goes on the mountain and the chassis goes upwards at the front, the boiler becomes level.
It's yet another brilliant solution that means Richard Moon's mountain dream can be accomplished.
Mobile 5 to Snowdon 1 and the summit past the 1 in 5.
As once again, this astonishing train achieves its mission.
Okay, ladies and gentlemen, welcome to the summit. Be very careful, there are high winds today. Mind the gap as you come off and enjoy your stay. Thank you very much.
So here we are, it's the end of July, unbelievably. We're at the summit of Snowdon. You get a real sense of why the original engineering team wanted to build a mountain railway to the top of the tallest mountain. It was not only a challenge, it was something they'd go down in history for. So, hats off to the Victorians.
On a clear day from this station at the rooftop of Wales, it's possible to see England, Scotland and Ireland. Richard Moon's 19th century vision created the journey of a lifetime. Mountain tracks. Railways traversing the peaks and troughs of the world's great ranges. Solving extreme problems in extraordinary environments.
You can see the cloud coming in. You can feel the temperature drop.
But sometimes, for trains, the answer can appear out of reach. Going uphill is all about grip. People are really good at it. Rubber-tired cars are pretty good at it. But with their enormous weight overriding their grip, trains are bottom of the class. This would pose a problem in Australia's Blue Mountains. A 3,500 kilometre long range on the country's east coast. In the 19th century, this natural wonder was a huge stumbling block for an essential rail line between Sydney and the resource-rich Lithgow Valley to its west.
The terrain in these mountains really poses a massive challenge to railway engineers. Trains are beasts which like to stay on flat, level ground. This terrain really turns that paradigm on its head. The sharp vertical drops in vertical elevation, they're all things that railways really don't like.
Tunnelling was financially unviable. There was no choice but to build a mountain railway like no other. The Great Zigzag. Completed in 1869, this remarkable Z-shaped track clinging to the mountainside is in an engineering league of its own for rail enthusiast and driver Lee Wiggins.
The Zigzag Railway deserves to be celebrated and known for its structural integrity and history, and the fact that it is still in existence and still going strong and still as strong as the day that it was built.
It was engineer John Whitton who believed the railway could take on the Blue Mountains. His smart Z-shaped design meant he was able to reduce the gradient to a manageable 1 in 42, meaning the trains had enough friction to ascend and descend safely.
Trains have a lot of problem working on grades that are too steep. You might not be able to start the train on a grade, you might not be able to stop the train on a grade if it's too steep. You're not able to carry as much freight, you're not able to carry as much load.
The shapes solved one issue, but Whitton also had a problem with getting trains to negotiate the track's acute corners. He achieved this by creating 2 reversing points.
Here we are at Top Point's reversing station. Normally steam locomotives would have come powering up the hill here, a locomotive at both the front and the rear of the train. As soon as the train would park up around the corner, the locomotive at the rear of the train would then take control, the points would be switched, and the train would come steaming off towards Sydney up in the other direction.
Whilst the railway may have been simple in theory, executing it in the Blue Mountains proved to be anything but.
When they were first surveying the route for the zigzag, the surveyors themselves were actually lowered off the cliff edge in wicker baskets down the side of the cliff face. After it was surveyed and the line was then designed, it was nothing but manual labour.
Such a colossal project required a huge workforce across the vast area. Luckily, the site offered a natural observation point.
So this seat here was cut into the rock by the engineers at the time that was constructing the railway, and it allowed them a great vantage point over construction. They could see right across the valley and see all different facets to be able to allow construction to take place.
In all, 85,000 tonnes of rock would have to be removed to cut the ledges for the track.
Where we're standing right now is a ledge. This ledge is where the rails run, and this was carved by hand. This was done by hammering drills into the rock and then blowing the cliff apart with gunpowder. Here we are, about 20 metres down from the top rock ledge, and we can see evidence here of the drill hole going all the way down to the base where the charge would have been loaded here at the bottom.
The work was so arduous that it took 700 men 3 years to complete the railway. Today, this group of volunteers is getting a taste of just how tough it was to create the drill holes for the explosives.
As you can see, what back-breaking work this must have been. Doing this for just 15 minutes really goes to show just how hard it was back in those days. No hydraulics, no mechanics, no engines, just good old-fashioned hard work.
Finally opened in 1869, the new cross-mountain route between Sydney and the Lithgow Valley proved an emphatic success.
The zigzag opening in the 1860s certainly benefited Sydney greatly and really opened the mining industry and the agricultural industry of the plainlands this side of the Blue Mountains. One of the first steel blast furnaces in New South Wales, if not Australia, was in Lithgow. So it really opened up the industrial, let's call it, revolution for Lithgow and the Central West area, and the zigzag was critical in achieving that.
Today, a network of tunnels cut through the mountains, and the zigzag is operated as a tourist attraction. Nonetheless, it remains an outstanding milestone for mountain rail lines.
To come up with something that drops as far as this does, to be built by hand by people hanging from baskets 700 feet above the ground, I think that needs to be recognised as a major engineering masterpiece of the 19th century.
Safely negotiating acute gradients is an incredible achievement. But this isn't an option for all mountain railways. When climbing steep slopes, something has to give. And often it's speed. So, when a mountain railway covers vast areas connecting cities and towns, and speed is of the essence, somehow its trains need to find a way to travel on the flat. Graubünden in southeast Switzerland. A region world-renowned for one thing. With such a mountainous terrain, you'd think cutting a railway through this dramatic landscape virtually impossible. But for well over a century, this centre of tourism and business has been connected by something truly mind-blowing. The Rhaetian Railway. An almost 400-kilometre network built to overcome nature at its most extreme.
The biggest challenge is the height. 30% of our railway net is 1,500 meters over sea level. So the climb, the weather, mountains, these are the big challenges.
It It was Dutchman Willem Jan Holtzboer who pioneered the railway's first line in 1888. The 50-kilometre stretch from Landquart to the spa town of Davos would spell the start of a railway phenomenon that now boasts 10 lines threaded through the region. And one of its most dramatic and demanding is the Albula line.
It's definitely not the easiest place to have a railway. I wouldn't say we are the toughest, but we are one of the toughest railway engineers here.
It's up to engineer Gilbert Zimmerman to keep the railways running.
The biggest challenge is the height. 30% of our railway net, it's above 1,500 meters over sea level.
Mainline trains are only capable of dealing with up to 7% gradients, so keeping the track as level as possible here means going through the mountains. With the original Albula tunnel over a century old, the team must build a new one through around 6,000 meters of complex rock.
We are going now into the tunnel, the Albula Tunnel 2, the new one. We started building this tunnel 2 years ago, and now we are in the geological fault zone, the most difficult part of the whole project.
The fault zone is full of water channels, creating problems for the team.
With all this water and soft rock, there's a big chance that it breaks down everything. So please don't go any further than here, because this is dangerous.
In these unstable conditions, blasting is out of the question. The team can only dig, and before this can start, the rock has to be strengthened.
We put cement into the rock with high pressure to stabilize the whole thing, to make it more harder.
Once firmed up, only up to 1 meter a day can be dug, despite mammoth machinery.
T-Rex is coming. Now we're going to see how it opens the rock.
To date, this painstaking process has managed to create as much as half a kilometre of tunnel. Not all of the excavation, however, is quite so labour-intensive. The team tackle this colossal project from 3 points. To the north and centre, soft rock requires digging, but to the south, harder rock allows a more dynamic approach.
This is the granite. It's a real hard rock, a dream of every miner, because it's stable, you can blast it easily.
And with today's blast, the miners have to clear a further 4 meters of tunnel.
We are drilling about 120 holes to blast. These holes we fill up with explosives, about 500 kilos. Every explosion, every blasting is exciting.
A blast this big requires a series of carefully orchestrated explosions, which can last up to 12 seconds.
This piece of cord connects the blasting master with the explosive material at the tunnel face. With this, he starts the explosion process.
With the tunnel clear,
we have right now the permission to blast. We are ready.
It's time for action.
3, 2, 1, go! Viva! I do this not every day, so my heart was beating a little bit faster.
As the dust settles, today's progress is revealed.
I'm really pleased right now. A clear face. The rocks are not too big. It's a regular hill of these rocks.
Once the blasting is completed, the new Albula tunnel will ensure high-speed trains can continue to travel on the flat.
A satisfying moment right now, just perfect.
high-altitude railways, pushing engineers to their limits as they tackle nature's most demanding terrain.
The zigzag is a major engineering masterpiece.
And one fleet of trains faces more problems than most. The Rhaetian Railway. One of Europe's greatest mountain networks, cutting through the heart of the Swiss Alps.
So you have been lucky. This is the Glacier Express, and now you smell food because they are cooking now for the guests on the Glacier Express. Yeah, that's true.
Whether tunneling beneath or crossing above, building a railway through these great peaks requires daring engineering solutions. Perhaps none more so than the town of Brusio, an alpine stop on the Bernina main line. Today, geotechnical engineer Kurdin Cantieni is making an inspection.
Here we're in the Poscavo Valley, a very steep valley that was shaped by glaciers during the last ice age, and those cliffs are still steeper than they actually should be geotechnically. That's what still causes rockfall.
With these unstable conditions, rockfall directly onto the rail track is a constant threat.
On the 14th of December 2008, about 40,000 cubic meters of loose rock material came off. You can actually see the spot up there where it broke off and covered the whole railroad track.
This catastrophic fall closed the rail line for several months. A solution was needed. On the mountain side of the track, an 8-meter trench has been dug to catch any rockfall.
If the dam wasn't there, especially the big boulders would be able to come down all the way into the valley bottom, eventually hit a house.
This engineered defense proved its worth in 2013, withstanding another significant landslide. Today, things are looking good.
So here we can see the railway. On the right-hand side, we have the slope with the old rockfall deposits. There are a couple of fresh stones, nothing big, so I'd consider it a normal situation.
The rock defense system is a brilliant solution to keep the rail line safe, but it's not the only railway structure that it protects. Brusio sits high above the valley floor on a steep slope, too steep for any train to negotiate.
To overcome that steep gradient, they could have built tunnels, but they already thought about tourism 100 years ago, and they wanted people to have the sights of the valley. So they really had to think about ways to make the railway go wide, so it doesn't have to go that steep over the cliffs here in the valley.
With space severely limited, getting any trains up or down from an elevated station seemed out of the question. Until engineers came up with an inspired innovation. The Brusio Circular Viaduct.
The Brusio Viaduct consists of 9 pillars. The train starts there, and it goes all along the loop, follows the viaduct, and then it is 20 meters higher in the very same spot, which is unusual for a railway, and then more or less flat into the Brusio train station.
With its 70-meter radius, this brilliantly engineered geometric shape and resulting gentle gradient ensures trains have an easy ride.
The problem might have been challenging, but the solution that they found was very easy. It's only a railroad track going in a loop, and to me it looks very beautiful. It is a very beautiful bridge, and it will probably outlast every one of us.
But elsewhere in the world, there are high-altitude ranges so hostile, they fill even the most daring engineers with trepidation. Picture battling rocky terrain and near vertical slopes for years on end. That's what it takes to complete a mountain railway. But before you celebrate, consider running it when winter descends. This can be a very different story. California's Sierra Nevada mountains, facing up to 20 meters of snow each year. It would seem like the last place on Earth to build a railway. However, in the late 19th century, the pioneers of California's Central Pacific Railroad thought otherwise. The railway was built to connect San Francisco to Utah via the Sierra Nevadas. By 1869, the section to Reno was almost complete. But there was still one major hurdle to overcome, as engineer Chris Potts is finding out.
This is Donner Pass, and this summit stood as the last major obstacle for the Central Pacific Railroad for joining California with the East.
Named after George Donner, the leader of a settler group, this 2,000-meter-high pass has an ominous history. During the winter of 1846, the travelling party became trapped by deep snow. After supplies ran out, to survive, they resorted to cannibalism. 24 years later, despite the evidence of impassable snowfall, the pioneering rail engineers pressed on.
Theodore D. Judah, the chief engineer for Central Pacific, thought that the weather up here would be no match for his railroad. Unfortunately, he severely underestimated the power of nature. Shortly after the completion of their railroad in 1870, many miles were lost under the snow, and it was deemed impassable.
Traditional snowplows relied on the momentum of the train and a wedge-shaped nose, which works a treat until the snow deepens and turns to ice. With no machinery to tackle deep drifts, Judah built 40 miles of snow sheds to protect the track. But these smoke-filled tunnels were a temporary fix. Finally, in 1883, Canadian inventor Orange Jull provided a solution with a groundbreaking machine. The rotary snowplow. A truly monumental snow battling solution.
This absolute monster of engineering is the last word in snow clearance. If there's a serious snowdrift, this is what the railroad rolls out. Amazing.
Today, the conditions may be fair, but riding this iconic machine is a once-in-a-lifetime opportunity.
This machine runs off of 1,500 horsepower, operated by that B unit right behind us. This plow can clear massive amounts of snow in minutes. What a feat of engineering. Absolutely amazing.
Unlike those traditional wedge-nosed snowplows, Jull's machine relied on an entirely different mechanism.
This fan works like a giant corkscrew. It cuts away at the ice bit by bit, and what it does is it turns the snow into a fine powder, and then through the centrifugal force, shoots it out through the top in either direction.
With Jull's 12-foot fan able to tackle even the worst build-up, it would revolutionize snow clearance.
So not only could this snowplow move more snow than traditional methods, it was also much safer. Not needing the momentum that more traditional methods needed, this was able to operate for longer distances and at lower speeds, meaning there was less of a chance that this would derail. Shortly after its introduction, the rotary snowplow proved itself time and time again in the most severe weather conditions.
In the winter of 1952, Smart Ridge near Donner Pass experienced a huge blizzard. The city of San Francisco streamliner was buried in around 5 meters of snow, trapping over 200 passengers. Although it took 3 days, no less than 4 rotary ploughs finally reached the train, saving all but 2 of those on board.
Since its introduction in 1870, the rotary snowplow has fought the worst weather and won. It truly is the ultimate snow clearing machine.
Mountain railways, overcoming mighty peaks, allowing millions to enjoy some of the planet's most mind-blowing scenery.
They wanted people to have the views of the valley. To me, it looks very beautiful.
But some railways aren't just for seeing the sights. Flam, a remote Norwegian community. Situated at the southern tip of the country's longest fjord, during the early 1900s, this isolated town was all but cut off from civilization. Connecting to the Bergen Railway 20 kilometers away would change their fortunes. But with the main line perched nearly 900 meters above, achieving this would be far from easy. As geologist Trina Heller-Simenez knows.
Here you can see clearly why it was so difficult to build a railway. You have really steep and very tall mountain sides with lots of fractures. And in the bottom of this steep valley you also have the river. So to build a railway, it actually had to hug the mountainside and wind its way upwards the valley.
Only an extraordinary feat of engineering would overcome nature this tough. The Flan Railway. One of Europe's steepest standard gauge train lines. Clawing its way up to the main line, crucially connecting Flam to the outside world. A journey that never fails to impress CEO Sivert Buck.
I would like to welcome you on board the Flam Railway.
The Flam Railway starts at 2 meters above sea level, and it goes through a typical Norwegian valley from the Ice Age up to Myrdal station at 867 meters above sea level. It's considered one of the steepest railways in the world.
In 1923, it was senior engineer Ferdinand Björk who was tasked with making the Flan Railway a reality. The 20-kilometer line from Sognefjord to Myrdal station in the mountains would pose enormous challenges.
You have these steep mountain sides. You have rock falls, avalanches when building. The climate in the upper parts is really Arctic. It's a really big challenge to do this thing.
Add to that waterfalls and treacherous ledges. To bypass as many obstacles as possible, Björk commissioned no fewer than 20 tunnels. Around 200 tunnellers were brought in to cut through the mountainside in grueling conditions.
My great-grandfather, he was building railway tunnels in the mountains. He always liked to tell stories and about how they lived. And the heaviest thing was to drill up in the roof of the tunnels. They had to do everything like up like this. It was very heavy work. I think it took like 1 month to drill just 1 meter of tunnel.
Today, with the train line complete, geologist Trina continues the family's railway tradition above ground, tackling a potential problem that could bring the mountain rail line to a grinding halt.
When you have such steep cliffs, it's obvious that you will have rock falls. There are lots of fractures, the mountains are very tall, so rocks always fall down. It's very easy that the railroad could be hit by rocks. So you can see actually how loose these rocks are. So these small things fall down. It can happen also to big ones.
And today, the team have spotted something that could spell danger.
What I've seen here is that there's a block with fractures on all sides. It's quite huge and heavy. You can see the train is just passing us down there. If one block like this falls down, it's dangerous for the railway and for the people, and we want them to be totally safe.
Rock fractures like this are often caused by a phenomenon known as frost wedging. This is where cycles of freezing and thawing water trapped inside the rock can cause it to break away.
So this is the block I think you should put 3 bolts in.
Combating this requires an ingenious solution.
This could be looser, but this is bigger. Don't you agree?
A traditional method dating to the 1800s, known as rock bolting.
Evel is now down checking how many bolts we shall have and that we agree and how the blocks look from down there. He's going to drill 3-meter and 4-meter long bolts into the rocks to fasten them to the solid rock. And then when you have the hole, you put in this glue. First it has to be mixed in there with the drill, and then you wait for a while, and then everything is glued. This is basically the technique that's always been done, that you fasten the rocks to the mountain.
With several kilometers of open track lying below, this preventative work is vital.
How's it going, guys? Everything okay?
Yeah.
Good. This work is really important because, you know, if any rails or anything is damaged, or even this overhead lines, you cannot take the train, so it's really important for the whole area.
The extreme scenery this railway once set out to conquer is now part and parcel of its success.
Flåm Railway has in the last 30 years transformed from a railway who took people from Flåm and made us go to Oslo or Bergen with the railway. And now it's more a tourist railway, and it's increased to about 1 million passengers this year.
All transported to the track's mountainous summit of Myrdal in a journey time once thought impossible.
Well, this morning it took us 50 minutes to get to Myrdal, and in the old days it would have taken a day or two to get from Flåm up to the mountains.
All down to generations of pioneering railway engineers.
Can you imagine more than 100 years ago that somebody stood here looking over the valley saying, like, we're going to build a railway here? That's impressive. This is one of the most remarkable railways anywhere in the world. And I'm able to take part of that. That's fantastic. I'm so proud of it.
Since the invention of the train, mountains have posed railways some of their toughest challenges. Sparking inspired solutions.
This plow can clear massive amounts of snow in minutes. What an incredible machine!
Taking engineering to new heights.
The people who decided to build it were taking a huge leap forward and a huge leap of faith.
Mountain railways all around the world really deserve to be celebrated.
To create impossible railways.
Throughout history, mountain railways have been an important tool for pushing through the boundaries for human exploration.
Following their meteoric rise in the 19th century, railways have become the transport arteries of the world. Built across every terrain, they've overcome almost all nature can throw at them. But there's one environment which is their nemesis. Some of history's greatest railway engineers have been pushed to their limits in the quest to conquer our water worlds.
The water here is very deep. An earthquake could cause a major disaster.
Brunel's job was to get from Devon over the Tamar estuary to Cornwall. Hell of a challenge.
There's about 11 lakes with difference of level. This is the problem.
When doing battle with a Waterworld, railways might face the odd obstacle. Steep cliffs, perhaps, or deep river valleys. Even sinking ground. Or demanding neighbours. Not to mention wild weather. But sometimes railway builders are faced with the full set. The famous rolling hills of Devon in the southwest of England. In the first half of the 19th century, engineers were faced with the seemingly impossible challenge of building a railway across this undulating county. Today, engineer Steve Hawkins is getting a bird's eye view of what his predecessors were faced with.
It all looks very picturesque now. Are we going right to left or? Yeah.
The initial plans required long tunnels and even sections where the trains would have to be hauled up steep inclines with ropes. But the project's engineer had an audacious plan to avoid the hills altogether.
It is a very unique piece of railway. It's unique that it runs right next to the sea for 7 miles.
By hugging the coast, the South Devon line could stay on the level. It's the brainchild of the world's most legendary engineer, Isambard Kingdom Brunel. But taking on this Waterworld with a railway would prove to be one of Brunel's biggest challenges, as today's engineers know all too well.
Brunel created that part of the railway 150 years ago plus. On a daily basis, the wave height and the strength of the waves can affect the railway, with the sea spray totally washing out and going over the trains.
This is one of the most unforgiving stretches of coastline in England. In 2014, it took just one of many poundings. Powerful waves destroyed the rail line at Dawlish, and landslides blocked the track.
It's the main infrastructure of railway into southern Devon and into all of Cornwall. That's for freight traffic and also passenger traffic, so it is key and imperative that we keep that traffic running daily for our customers.
Although sea walls, tunnels and rock armour have been used to protect his line, more than 150 years on, it's a constant battle for engineers to keep Brunel's impossible railway running.
Based on recent inspections, we've noticed that there's some degradation of the netting system. So what we'd like you to do today is just check for any componentry failure, make sure that it's still fit for purpose.
It's down to 21st century engineers to keep Brunel's 19th century dream alive.
There are 6 different types of mesh systems or structures in place to stop any landslips landing on the track and derailing trains.
This is the problem area. This is all covered up.
Rock anchors have been put into the cliff face and the netting surrounds the slope around it to basically hold the slope in place.
Yeah, well, it's pulled the edges apart there as well, hasn't it?
Stitching going.
The wire netting combined with barriers and motion detectors form an engineering solution that means Isambard Kingdom Brunel's Victorian vision still plays a vital role in Britain's modern rail network. But further down the coast, the emphasis is on running another extraordinary section of Brunel's line, in a way that he may have found more familiar. Having conquered the Waterworld for his South Devon main line, Brunel tried the same again with an ambitious branch line. The Dartmouth Steam Railway was designed in 1857 and now runs from seaside Paignton to Kingswear and the historic natural harbour of Dartmouth. Today it's run as a heritage line.
It's quite an art to controlling a steam engine.
Preserving another section of Brunel's impossible railway.
This is one of the major issues for us, hugging the coastline as we do. As you can see, we're right next to the sea here. The cliff face is, what, 15 feet away? So this gets the ravages of the winter.
Weather conditions do have an effect on driving techniques.
When designing the route, Brunel had a scheme to at least make life easier for himself by the Dart estuary.
Originally, Brunel was going to bring the railway across here, this is the Greenway, and go down the river, and you can see there's an inlet, that's actually Old Mill Creek, a viaduct there, and then where you can see in the far distance a naval ship, that would have then taken the track into Dartmouth.
However, Brunel's plans were thwarted when he wasn't allowed to bridge the river, resulting in one of the railway world's most bizarre honours.
Brunel actually designed and built the station down at Dartmouth, and it's actually in the Guinness Book of Records because it's the only station that's never had a train call upon it, because in fact they built that before they got the permission for the line. Consequently, there was a full waiting room, ticket office, actually on the Dartmouth side. Instead, he was forced to come down this side.
Brunel would have to tame the area's natural obstacles. First digging through the hills with a 450-metre-long tunnel. And then building an epic stone viaduct of the same length over the valley.
We consider ourselves very lucky on this railway. We do have some rather marvellous scenery.
An engineering challenge is to get the materials to site to build that viaduct is quite phenomenal. It really is in the back of nowhere. So yeah, huge amount of work went in just to build that one viaduct.
One of Brunel's biggest challenges, however, is virtually invisible.
Before the railway came, this whole area around Goodrington would have been a salt marsh. Goodrington Beach, as we see today, is not there. This whole area leading about half a mile up inland was a complete salt marsh.
The deep, soft marsh would swallow up any tracks or trains laid across it.
They had to build an embankment. Fortunately, there was a huge amount of spoil available, but as they were putting it in to make this embankment, it was just disappearing down into the salt marsh.
Brunel's solution was to run drainage pipes below the marsh.
Underneath this whole valley, there is still Brunel's original pipework, draining the valley as it has since 1860.
And as a welcome byproduct, the works created one of the region's most popular beaches.
So, Mr. Brunel, congratulations.
The line became fully operational in 1864. And nearly 160 years on, despite the conditions, Brunel's perhaps most picturesque of engineering achievements is still going strong.
It is stunningly beautiful. I'm very biased, but when you go from the coast into the inland river of the River Dart, which is completely unspoiled, it is one of the most beautiful places.
I like the fact that we're basically living history. Steam engines have been around for 150, 160 odd years.
We're keeping bits of history alive.
Railways are taking on the water. inspired engineering, revealing some of nature's best-kept secrets.
We consider ourselves very lucky on this railway. We do have some rather marvellous scenery.
But some Waterworld railways test even the most seasoned of engineers. On the southwest coast of Britain, Isambard Kingdom Brunel's engineering ingenuity had conquered much of this impossible water world. But one major obstacle still stood in his way. If he was to take his railway into England's most westerly county of Cornwall, he would have to cross the River Tamar. Engineer Peter Cook has worked at the site of Brunel's proposed bridge for the past 5 years.
Brunel's job and challenge was to get the Great Western Railway from Devon over the Tamar estuary to Cornwall.
Not only is the Tamar a wide and deep waterway, but it was, and still is, a vital thoroughfare for the Royal Navy's Plymouth-based fleet.
It couldn't put numerous piers across the river because that would inhibit access for the Navy at the time, as they insisted that they needed a 100-foot clearance for their tallest ship to pass under the structure. Now at the time, technology weren't available to generate, as we know, a traditional suspension bridge due to the anchorages that would be required. The technology just wasn't there. So his solution was to build this. Superb. I've worked on this structure for over 5 years. I know every nut and bolt on it. It looks wonderful.
Completed in 1859, the Royal Albert Bridge was Isambard Kingdom Brunel's last great achievement. A single midstream pier supports 2 spans of 139 metres each, both crowned with giant wrought-iron tubular arches. It's a design unique to the world.
If you can imagine, each span were built individually. The Devon span were built on the Devon shoreline, the Cornwall span were built on the Cornish shoreline, and then floated in position on barges. You can imagine in the 1850s, there's no diesel engines as such, all ropes, steam power. What a feat of engineering. It's the best bridge in the world.
And it contains very clever and innovative design features to get over all the challenges that the estuary and the Navy presented. In fact, it has been described as 3 bridge designs in one, none of which would work without the others. With a traditional suspension bridge, the load from the bridge deck is transferred through the chains and vertically down the piers into the bedrock below.
One of the reasons why Royal Albert Bridge was never a traditional suspension bridge, in 1850s, we didn't have the technologies to insert suitable ground anchors to form a traditional suspension bridge. So therefore is left with a very unstable structure, as you can see. So if you can imagine load imposed onto the deck, the piers would just bend. Catastrophe. So to counteract that, Mr. Brunel, in his wisdom, inserted a boat at the top. Now this does increase stability. The piers are now much more solid, although the lateral movement is still the same, which is unsuitable for passage of trains. So to counteract that, Mr. Brunel inserted on the Royal Albert Bridge vertical hangers connecting the top truss to the lower sections of the bridge. Already the structure's stiffening up significantly. Just bear in mind all this is happening in 1850, which is a marvellous feat of engineering, to say the least. It'd be a major project in today's times. On the Royal Albert Bridge itself, there's 11 of these hangers on each main span. You can imagine a little train comes along. The load imposed by that is distributed by the bowstring truss along this bow and then down each pier, enabling safe passage of trains for the last 150 years. Brilliant structure, unique.
Despite virtually being on his deathbed, Brunel insisted on crossing his final masterpiece himself. In May of 1859, he lay on a specially designed open wagon as it carried him across the bridge. He died just 4 months later.
I've worked on the bridge for 5 years, but funnily enough, this is the first time I've ever been on a train across the structure. It's quite exciting, really.
150 years on, it is still achieving the impossible.
Isambard Kingdom, Brunel's, arguably is his finest structure ever built. I love this bridge, it's brilliant. It's the best structure in the world. Unique.
Daring engineers are building their railways across challenging waterways. But there are some Waterworld railways that defy expectation. Expert Krzysztof Kowalczyk is in remote northern Poland, where in the mid-1800s engineers decided to build a series of canals to join the seaport of Elbląg with the rich timber region of Ostróda.
Since 16th centuries, trees from this area was very expensive because there was the best raw material for the mast to the ships.
But standing in the way was a 10-kilometer uphill stretch. A total rise of 100 meters.
On this distance, on this difference of level, the locks was impossible because there were 32 locks on the distance 10 kilometers. Locks take too much water and there was too many locks.
It was down to Prussian engineer Georg Jakob Stenker to find an answer to this seemingly impossible problem. And today, 150 years later, skipper Bartek is about to face the obstacle that stood in his way.
Tak, powoli się zbliżamy.
And Stenker's extraordinary solution.
It is the most strange railway in the world. This is not for any kind of train. This is for boat, for ships. It's only one working in the world, system like this.
I już wtedy pojedziemy, nie popłyniemy, a pojedziemy.
Georg Stenker created a railway capable of lifting boats out of the water and carrying them up and down hills.
Wózek przetransportuje nas na drugą stronę górki.
There are two parallel sets of track, each with a wagon capable of holding a 30-meter-long vessel. The two carriages are connected by a looped steel cable.
Taki wózek waży około 20 ton.
This cable is, you can see, have to be very strong to pull a carriage with a ship which is weight about 50 ton. It's a lot.
Są to wózki oryginalne.
This amazing solution to connect these canals, there was just slipway. Slipway like this, with dry hill. There is one canal, another one canal is about 20 meters lower, and that was the great solution.
5 of these boat railways sit along the 10-kilometer journey, lifting the boats in a series of steps to the summit.
When the ship coming on the carriage and connect to the carriage, the man from the ship is coming and ring the bell. So operator know that he is ready. When he is ready and everything is okay, operator giving the signal with the bell to the operator in a machine place.
And it's no ordinary machine.
That's a water wheel. That's an engine. That's giving the power for all this system for pulling the 50-ton ships 20 meters up to the next canal.
Cleverly, Stenker's railway harnessed the massive potential energy of waterways themselves.
You can feel the vibration, how it's working. It's amazing this building still exists. It's not destroyed by this vibration. You see, in one of this wing is capacity about 1 ton of water. So in one moment, 3 are full. So 3 tons of water is turning this wheel. Wheel is about 8-meter dimension. It's more than 4 meters wide. You never saw a bigger water wheel than this.
The wheel is used to wind the massive lifting cable.
This is the heart of the system. You can see this drum with the line. This is one line. Everything working with power of water. Miracle! That's amazing.
Each wagon is counterbalanced by another, traveling simultaneously in the other direction.
Jesteśmy gotowi do przeprawienia przez górę.
This ingenious system can transport skipper Bartek and his boat over each of the 5 inclines in only 30 minutes.
Właśnie, musimy się już powoli na wodzie. Zostawiamy wózek za sobą.
From its opening in 1860, the incline lift system transformed the region. It was now 5 times quicker to transport timber to the coast, and the Elblag Canal became one of the longest trade routes in Poland. As the road network grew, however, it fell from favour, until one forward-thinking man intervened.
He named Adolf Tetzlaff. Adolf Tetzlaff had 8 children with first wife. With second wife, he have also 8 children. He have to find idea how to earn the money. He found idea to bring the tourists on the ships. And he rebuilt one ship for tourists and start to transport tourists on canal. And that was a very good idea.
Today, tens of thousands of tourists every year ride Georg Stenker's impossible boat railway.
Engineer Georg Jakob Stenker, thanks him, we have this original. It's absolutely amazing because it's one in the world and it's still working.
Waterworlds push railways to their limits. Overcoming the elements. Challenging engineering's greatest minds.
What a feat of engineering. It's the best bridge in the world.
And there are some railways that face the big blue head on. Railway engineers can tunnel through pretty much anything, no matter what's above, how much room there is, or even what lies outside, as long as nothing moves. It's a problem that faced Istanbul in Turkey. This ancient metropolis lies in both Asia and Europe, but is split in half by the mighty Bosphorus Strait. For the city's 15 million inhabitants, this vast waterway poses a problem.
Crossing between the 2 parts of this city has always been a problem. The bridges just can't cope with the volume of the traffic, so it's always congested.
A rail tunnel to connect the city and ease the traffic has long been a dream. But as engineer Atsushi Nishikori knows, building under this stretch of water is about as challenging as it gets.
The water here is very deep, 61 meters. There's strong currents in both directions. There is a constant flow of ships to deal with.
But there's one problem that makes this underwater railway challenge a seemingly impossible one.
Crucially, we are close to big fault line, so earthquakes are common.
Boring a tunnel in a seismic zone would be out of the question. Added to that, the deep, fast-flowing water meant that there was only one solution.
We knew we had to use an immense tube tunnel here. It's the only method that can cope with both the deep water and earthquake condition.
The Marmarai Tunnel would need to be the deepest immersed tube tunnel in the world. A 1.4-kilometre-long series of pre-made concrete and steel tubes running under the Bosphorus Strait, sunk to depth never before attempted.
This method is normally used only in up to 60 meters of water. And we were trying to go to 61 meters. So we were pushing deeper than anybody had gone before.
Each tunnel section is floated into position, then sunk, and then connected to the others. A clever solution for the construction, but when finished in 2013, this sub-aqua railway would still be in constant danger from earthquakes.
An earthquake could cause a major disaster. Any small spirit in the tunnel could cause a massive flood that would totally destroy it.
İzzet Yüksel must constantly monitor a series of cutting-edge engineering solutions incorporated to keep the railway safe.
Our tunnel is well equipped to deal with big earthquakes. We have got lots of seismic sensors all through the tube tunnel section, and that computer gives decision whether to continue the operation or make all the passengers and staff go out of the tunnel.
But should an earthquake hit, the tunnel is well prepared.
Now we have got gaskets in between each tube sections. In fact, this is one of those points, and with those gaskets, our tube section is flexible for earthquakes in Istanbul.
Each of the 11 tube sections is connected on the seabed with a steel and rubber gasket. If an earthquake strikes, the tunnel can flex and bend without breaking. This flexible tunnel is crucial to the project's success. Should the worst happen, however, high-powered pumps kick into action. And there's one final line of defence: the Marmarai's mighty floodgates.
Totally, we have got 4 floodgates, 2 in İskirkeci and 2 in Üsküdar stations. They are huge floodgates, they are steel construction, and for each square centimeters, they can handle 1 ton of water pressure. It's very easy to close the gates if there are no trains, but if there is a train, then some closing procedures come into account. They are definitely the last line of defense for water.
Through daring engineering, the team in Istanbul have created an earthquake-defying underwater railway, enabling travel across the city and beyond.
To build tunnel under the Bosphorus, we challenged many issues, then finished the project successfully. And this is the first underwater train tunnel in the world between the continents. So we are very proud of this achievement. In future, I want to come back to Istanbul and get on the Marmarai and then travel underwater anywhere in the world.
Engineers have taken railway solutions to new depths. But bridging some troubled waters is a seemingly impossible task. The Polk Strait, part of the mighty Indian Ocean that runs between southern India and Sri Lanka. Almost 150 kilometers across at its widest point, it's peppered with tiny islands. And connecting to one of those islands is the iconic Pamban Rail Bridge.
This was India's first sea bridge, and it's still the queen of Indian bridges.
Opened in 1914, this 2-kilometre cantilever crossing connects Mandapam on the Indian mainland with the island of Pamban.
The Pamban Bridge is this immense structure that really helped ease the journey between India and Sri Lanka, which until then had been a grueling journey by boat.
Not only is Pamban a stepping stone to Sri Lanka, it's home to a prominent Hindu temple. So creating a permanent link was crucial, although far from easy.
The Pamban Bridge is a real feat of engineering. So first of all, it had to cover a huge distance of over 2 kilometers. Then it was built over the sea, and the sea can be rough, unpredictable, and it's an incredibly corrosive environment. Then add to that the fact that it's actually a windy environment which is prone to cyclones.
In 1911, it was Mr. J.T. Lewis, chief engineer of the Southern Indian Railway, who took the job. And with a seabed of unstable reefs, he opted for a light multi-span steel bridge. All 45 deck girders were delivered pre-made and floated into position, then lifted onto the masonry piers. And to avoid blocking the channel to shipping, he installed a rather cunning lift bridge.
So the lift bridge, which is also called the Scherzer Bridge, is a double-leaf bascule bridge. And if you imagine, if you're sitting on a rocking horse and you lean backwards, then the front of the horse actually lifts up. And it's the same principle that's applied to lifting up these bits of the bridge.
Each bridge leaf is wound open with a system of counterweights. As it's wound, it rolls back on its curved base, letting the weights take over, opening the bridge to let ships pass. Its ingenious design means it's very easy to operate. This enormous bridge can be wound open by hand.
I find it completely fascinating that over 100 years later, they still use the same methodology and it still works. To build any bridge in this environment would have been incredibly difficult, but to have built a lift bridge was such a monumental achievement.
Today, the rail bridge remains the second longest sea bridge in India, surviving monsoon, cyclones, and the ravages of the sea.
The fact that the Pamban Bridge has lasted for so long is a testament to two incredible facts. The first is that it was built in a really robust way, and the second, that it's been really well looked after. This is a really extreme environment, and it really took some brave engineers to make the decision to build here.
Water. A railway's greatest adversary, inspiring great engineering solutions to keep trains on track.
We were pushing deeper than anybody had gone before.
But there are some Waterworld problems that need extreme railway solutions. Cinque Terre on the Italian Riviera. This UNESCO World Heritage Site is made up of 5 ancient villages, clinging to the near vertical cliffs overlooking the Mediterranean Sea.
In Italian, cinque is 5, and then terre is lands. We have the villages of Monterosso, Vernazza, Corniglia, Manarola, which is behind me here, and Rio Maggiore. The villages are about 12 kilometers apart. It doesn't sound like a lot of space between them, but if you're trying to walk it, it's incredibly steep.
For centuries, these communities were cut off from the rest of the world. And even today, their remoteness is still being felt.
At the end of the 19th century here, it would have been very difficult to travel between the villages because the only way to do it was on foot or by boat, which is always contingent on weather conditions and sea conditions. It wasn't uncommon for people to marry amongst the village. In fact, when I moved here and married my husband, who's from one of the villages, an elderly woman told me, "Oh, you're bringing fresh blood."
In the late 19th century, daring engineers wanted to attempt to connect the villages by train. But the rugged Ligurian coastline is no easy place to create a rail line.
As long as man has been in this area, there's been difficulty with the sea, just because it's always an unpredictable element of nature. The terrain here is incredibly rugged. We don't have rolling hills, we have crumbling cliffs. Everything here is just a little bit more difficult than other places in the world.
In 1874, a team of courageous engineers completed the seemingly impossible. The Cinque Terre Railway. A 44-kilometre rail line carved through the cliff which would finally connect all 5 villages.
To build a railway here in the Cinque Terre, it was very courageous and a bit crazy, to be honest. We have extremes, we have the cliffs, we have erosion, we have rough seas.
To protect the new rail line from the storm-scoured cliff face and the unpredictable waters, there was only one solution.
The engineers, while they were constructing the line, tried to hug the coast, but they had to burrow tunnels through.
This 44-kilometre rail line includes no less than 51 tunnels, making a grand total of 28 kilometres, all drilled and blasted by hand. This ambitious tunnelled construction means the railway has stood the test of time. And today, the job of looking after it falls to engineer Luca D'Angelo and his team.
Salve, molto piacere, Luca D'Angelo. Ok, ti ringrazio, Fabrizio. We are on the top of Monte Rosso. We are working in several places here. Between Monte Rosso and Vernazza, we are going to build some drainage works to protect our tunnel from the water coming down from the mountains. And we are going to deliver these steel bars. They are quite heavy. You can see it, and you cannot really bring these by hand or by the path.
To deliver heavy materials to clifftop work sites, engineers become more like action heroes.
Yeah, we have helicopters that helps us a lot now during our works. And I can't imagine how they could build this line with just by boat and carrying materials. It was something of crazy, I think. I think it's amazing to see also this piece of railways. Even if the most part of it is in tunnel, when you see the open, it's like amazing. This is an artificial tunnel, but made the beginning of the construction of the line. You can see the windows here from which train passes through. They had to build almost all the railways in tunnels to prevent the risk of rocks falling down from the slope.
The few areas still open to the elements are also slowly being covered by the team.
As you can see, we are on a bridge, and to protect our infrastructure between the two tunnels, we had to build a steel structure made by column and beams and then concrete slab. You can see here rocks falling down, but not only rocks, also floating from the top of the mountains.
But the tunnels themselves are still prone to the ravages of nature. Some have been closed and replaced, and the rest are protected by a complex drainage system to deflect seawater and overflow from the rivers above. But there are some big water events for which no one can prepare.
On October 25th, 2011, a terrible flood struck here in Vernazza. It was a place that you wouldn't recognize today. Mud filled up to the first floor of the buildings. There were locals that lost their lives. The village was absolutely devastated. It looked like a war zone. The railway station in Vernazza was completely covered with rubble. The tunnel that connects the villages was covered with rubble. The only way to reach the village during that time was either by air or by boat.
Torrential rain had flooded the rivers above, washing debris from the vineyard terraces into the drainage channels. As the channels became blocked, both town and railway were flooded. Luca and his intrepid team are making sure this never happens again.
We are on the top of the railway tunnel. We are going to build a protective structure because if you can see here, we have like a channel that just undergoes the railway tunnels. In 2011, when there was a huge flooding, mass rock falling down just closed this channel, and the flooding was going inside the tunnel, and the line was out of order for like 1 week. And so what are we doing now is going to build a structure to protect our infrastructure and to be sure that it will not happen again anymore. This work is essential for sure. But we are now going to carry out a huge number of works like this, obviously with the use of helicopter. As you can see, it's the only way to bring material here. We need to move.
Today, the Cinque Terre Railway is used by locals and tourists alike and remains the best way to explore this spectacular corner of the world.
Right now, we are in one of the 51 tunnels along the line. Every once in a while, there'll be a glimpse of the seaside, maybe the village. We're right on the water's edge. I remember the very first time riding on the Cinque Terre train and being in a tunnel and then having a flash of paradise. It really is beautiful.
And Luca continues to support the work of the railway engineers who dared to build it in the first place.
I think this is one of the most challenging and impossible railways. As you can see, they had to face like a lot of problems, engineering, designing, but also the construction. They did a great job in the past. It's one of the most challenging railways for sure. I think it will last forever.
Since the dawn of the railway, water has proved to be its fiercest opponent. Calling for daring solutions.
It had a number of challenges, not least the fact that we are hugging the coast, but thank God they did it because we have a beautiful line to enjoy today.
Taking engineering to a new level.
This job was very difficult. There was a huge number of workers and engineers taking part of this project. The engineers were the best in the world at that period.
To create impossible railways.
Water is the biggest challenge on Earth for any railways. But thanks to brilliant engineering solutions, our trains can conquer the water in all sorts of ingenious ways.
For over 150 years, our railways have been pushing engineering to its limits in order to open up our world. Driven by progress and a thirst for adventure, trains can now travel further and climb higher than ever before. But for train engineers, there's one ambition that's perhaps their biggest driving force of all: the need for speed. Shaping the iconic machines of the past, producing innovations for the future. But making trains go faster poses a unique set of challenges.
If you hit very many speed bumps at these ultra-high velocities, you will not survive.
When you have a train very powerful and very light, you need a special balance between grip and power.
When our train rushes into the tunnel with high speed, the shockwave on the exit, we can get a big bang.
The trouble with most trains is they only have one engine. So the longer you make them, the loco must take the strain.
Hello.
But if there's a need for speed, there's only so big an engine can be. The birth of our railways and the steam locomotive go hand in hand. For over a century, across the world, these iron workhorses graced our rails. But by the 1930s, in the UK, these mighty machines faced a seemingly impossible challenge. They needed to go faster. As rail journalist Tom Bright is finding out.
Passengers at the time wanted their trains to be faster, more comfortable and more luxurious. So they introduced more facilities on their trains, such as dining cars and luxury saloons. But that meant trains got heavier and therefore slower.
The once thriving rail networks were under threat from newer, faster road travel, and the rail companies were fighting for fares. The most hotly contested route was between the two great capitals, London to Edinburgh. To make this near 650-kilometre journey at speed in a steam train weighing several hundred tons would require a locomotive like no other. And in 1935, it was the A4 Pacific class that would change everything.
They brought improvements in speed and power that the world had never seen before. The A4s were the ultimate in express passenger locomotives.
Its designer was one of Britain's great railway pioneers, Sir Nigel Gresley. Gresley had already designed the legendary Flying Scotsman, an A3 class locomotive.
What Gresley did with the A4s was bring together all his existing ideas. In effect, the A4 is an A3 GTI, a souped-up A3.
The secret to the A4's power is the unique combination of innovations.
He was really pushing boundaries. With the A4s, he opted to have 3 cylinders. With 2 cylinders, the locomotive tends to wobble at speed. With 3, it's much more balanced.
Gresley's 3-cylinder formation produced smooth power, and the wheel configuration made the most of it. 4 small at the front, followed by 6 enormous driving wheels, giving 50% better grip, and 2 smaller rear wheels, which allowed space for a larger firebox. It meant more steam, more power, and so much more speed. After recent significant repairs, today a group of engineers and enthusiasts are firing up the Union of South Africa, one of only 6 remaining A4 super engines.
Needs just a little bit more, mate. About 3/4 full.
And it's a rare return to service for this 80-year-old powerhouse.
Basically, we're lighting the fire. So we've laid coal in there, we've put wood on top, and now we're using paraffin-soaked rags on top of that to get everything going.
Main priority is water's in the boiler. We definitely need water in there. Make sure it's fit to run, really.
Shut the top, please.
When you're pulling away, you've got to be very, very gentle with the regulator. It's got so much power, it'll wheel spin straight away if you gave it everything. Here, we're only, unfortunately, allowed to do 25 miles an hour. You're having to hold it back, really. It's such a powerful beast.
For today's trip, they're joined by the Union of South Africa's owner of 50 years, John Cameron. And it's an anxious wait, hoping that his antique train has still got what it takes.
That's one of my concerns, that it's working and that it won't fail. It won't sit down, as we say.
There are hundreds of rail fans hoping for the experience of a lifetime.
That sound you can hear is the singing that you want to hear, so you know the injector's on. Once you've got that, then you know you've got your injector on.
There's a lot riding on this mighty machine's historic engineering still working.
Well, you know, you've a lot of power
at your command, so you've got to use it sensibly.
Trying to get a feel for the regulator. Shortening the cut-off so we don't need so much steam.
You always have to know your locomotive and know how it's going to respond, whether you're starting off, running at speed or braking. I mean, there's no two locomotives behave the same, even though they're same class.
Gresley had created an engine of immense power. But before he could test it out, there was one more problem to overcome: the shape of the nose.
Gresley took his formative design into the wind tunnel. This is something that had never really been done on locomotives before.
The traditional flat nose was replaced with a wedge-shaped nose to decrease wind resistance, but crucially, lift the smoke and steam away from the cab. In 1938, equipped with this perfect blend of engineering, the A4's Mallard reached 126 miles per hour, becoming the world's fastest steam train, a record that still stands to this day. Gresley's A4 design easily outstripped his competitors in both speed and style. Passengers could now travel on the East Coast Main Line from King's Cross to Edinburgh in only 6 hours.
When Mallard broke the world speed record, then that gave the A4s another bit of added attraction, if you like. But I mean, the potential for doing speeds in that magnitude is certainly still there today. So when you're on a line like this, some people might think that you're just pottering along. But actually, there's just about as much skill required to drive carefully and efficiently at a lower speed, to make the job go well.
And today's run has done the team proud. Gresley's super high-powered design achieved the impossible. The speed of the mighty A4 locos helped revive the railway, bringing passengers back on board. And his creation still continues to amaze to this day.
Union of South Africa really is one of the best. She is absolutely lovely.
Speed, the ultimate ambition for some of the world's greatest railways. Posing engineering problems that require new solutions. To take trains and passengers faster than ever before.
It's such a powerful beast, way ahead of its time, really.
But one railway's quest for speed is so extraordinary, its problems are seemingly impossible to overcome. If speed is the only goal, come on! The faster you go, the bigger the problems. Any curve is out of the question. Even the tiniest bump has to be ironed out. And then, of course, stopping can be the biggest challenge of all.
Uh-oh.
The Tularosa Basin in New Mexico is a vast, isolated wilderness. But it is also the unlikely setting for a record-breaking railway. Hidden in the depths of the desert lies one of the most extreme rail tracks on the planet.
We're at Holloman Air Force Base, New Mexico, at the high-speed test track, where we push the bounds of speed. And we use this, the most incredible railway in the world.
Built in 1949 to trial new aviation technology, this extraordinary 16-kilometer rail line pioneers extreme speed, propelling its rocket sleds to around 2,900 meters per second.
In total, we've broken the land speed record 7 times and currently hold it at over 8 times the speed of sound. It's no exaggeration to say we make history here.
But with the sleds covering the equivalent of over 30 football pitches per second, the engineering challenges are seemingly impossible. If the railway track isn't perfectly engineered, the consequences will be catastrophic.
Any deviation in that rail is an impact load. It's basically like a speed bump in a parking lot. And if you hit very many speed bumps at these ultra-high velocities, you will not survive.
The extreme range of desert temperatures means the rails must be pre-tensioned to avoid any expansion and contraction. The continuous welding along the 16-kilometre length ensures arrow-like straightness. But all of this is secondary to the most crucial engineering of all. The challenge of making sure each sled sets out and sustains a perfect trajectory.
This sled's going to be tested at Mach 4. In order to survive and maintain its path down the track, the sled has to be aligned to within a few thousandths of an inch. Failure to maintain that alignment could result in the sled exiting the rail. It could destroy the track. The way that we maintain that is we use a laser 3D tracker to verify its alignment.
With over 10,000 test runs completed on this phenomenal railway, the test track sled park is the resting place for speed machines once used to test vital areas, such as parachute deployment and pilot ejector seats.
So we've got the A10, F15, F16 here that all run down here at the track. Right here behind us, we've got the Sonic Wind replica. This is an example of the sled that ran down the track, specifically designed to see the factors affiliated with undergoing large Gs.
In the 1950s, the Sonic Wind No. 1 was piloted by Lieutenant Colonel John Stapp. His goal? To establish the effects of extreme acceleration and deceleration on the human body. In 1954, a 1,017-kilometre-an-hour run made him the fastest man on Earth. Incredibly, from this mind-blowing top speed, he was brought to a standstill in under 1.5 seconds, thanks to an innovative solution. A water trough braking system, positioned within the track.
He basically underwent up to 40 Gs of deceleration during his last ride.
Battered and bruised, Stapp's mission was nonetheless an important milestone in improving safety for airmen and pilots. Today, unmanned sleds reach almost 10 times the speed of Stapp. Although this rail line is precisely engineered, the sleds themselves require a genius innovation to survive the brutal stresses of a run.
We don't use wheels because of the ultra-high speeds that we travel at. You simply couldn't keep the sled on the track. So what we use are slippers.
Attached to the bottom of the sled, the metal slippers are curved around the head of the rail. As the sled gains speed after launch, aerodynamic forces lift the sled from the rails until it's stopped by the slipper.
So once a sled takes off, it doesn't actually slide on the rail. It kind of floats. There's very little contact with the rail. A good example is if you ride a new modern roller coaster, it's a very smooth ride. But if you ride an old wheeled roller coaster, it's a really bumpy, rough ride. And that's exactly what the sled experiences out on the track.
For over 60 years, this game-changing railway has achieved what was once thought beyond the realms of possibility. And it seems, for the Holloman high-speed test track, the sky's the limit.
So the next goal is Mach 10. Just to put it in perspective, that's going from this point to the very north end, 10 miles away, in about 5 seconds. So anyone that needs to go fast, they look to the Holloman high-speed test track.
I believe this is the most incredible railway in the world. I wouldn't want to be anywhere else.
When speed is top of the agenda, railway engineers undoubtedly face some of their toughest challenges, and none more so than the lie of the land. It was the challenging terrain of Britain's South Devon coast that drove pioneering engineer Isambard Kingdom Brunel to create an extraordinary superfast railway experiment.
So it's 1844, the railway had just made its way, edging closer and closer to the west of England. Brunel then wanted to take it further. He wanted to get his track all the way down to Plymouth.
But with a long stretch from Newton Abbot to Plymouth, renowned for its hills, Brunel had concerns that traditional locomotives would struggle with the steep gradients. To create power and speed, his solution was a recently developed concept: the atmospheric railway.
So the atmospheric railway was based on the principle that you can propel an object using atmospheric pressure if you create a vacuum in front of it, so it will propel itself forward.
Doing away with the locomotive, Brunel attached a piston from a carriage into a sealed tube between the railway's tracks. A pumping station positioned along the line pulled the air out of the tube, creating a vacuum in front of the train. Atmospheric pressure behind then acted on the piston, providing motive force, pushing the carriage along the track.
Here we have one of the largest remaining pieces from the atmospheric railway itself. Each section is 10 foot long. Inside here, this is where the air would have been. And we've got the slit in the top, which is where the piston from the carriage would have come all the way down.
Air leaking out of the slot was a major problem. The solution was to fit a leather flap along its entire length. As a malleable material, small wheels would reseal the slot once the piston had moved on. It was undoubtedly an ambitious design, but proved incredibly fast for its day, propelling its carriages to almost 110 kilometers an hour.
What I've got here is a small-scale model. At the moment, it's all under normal atmospheric conditions. And when I turn my engine house on, that's going to pull all of the air from this side of the tube, and that is then going to create a vacuum. That is going to draw the piston inside all the way along. And as that pulls it along, that's opening up just that section there, and this section here is resealing itself as it goes. Okay, let's see. Okay, and again, you can see how fast it really would have gone. And you can see why Brunel was quite excited by this idea.
It may be impressive on the flat, but how would it fare against the challenge of Devon's hills?
I think Brunel would be proud. Yeah!
The atmospheric railway's speed and ability to travel uphill offered exciting potential. But it had an Achilles heel. The slot's leather flap attracted gnawing rats, and consequently, sealing the system proved virtually impossible. As costs spiraled, after just a year, the line reverted to traditional locomotives. But almost 170 years on, in Northern California, Brunel's atmospheric dream lives on.
This is the Vector 1/6 scale test track. The track is about 2,000 feet long, a little over 600 meters, and it runs at about 30 miles an hour, which scales up to about 180 miles an hour in the full-size version.
Complete with graded hills and 180-degree curve, Eric and Max Schlinger's futuristic railway signals what they hope will be the revival of the atmospheric technology.
Basically, we did exactly the same thing that they had done in England. However, at the same time, we were working on high-strength magnets and found that we could do a lot of things they weren't able to do in the 1840s.
Whereas Brunel's tube ultimately failed because of its leaky leather-lined slot, the Vector's tube can remain permanently sealed thanks to magnets, which attract the train to the piston.
So what we have that Brunel did not have is the high-strength magnets we use to couple the thrust carriage to the passenger car itself. That magnet is really what makes the system work, and when we combine that by coupling the passenger car to the thrust carriage, we now have a system that moves on atmospheric pressure. So now that we have it coupled, all we really need to do is add a bit of air pressure, and the train moves.
When scaled up, the pilot model uses the same principles of pressure adopted by Brunel. And with no locomotive or traction motors on board, minimal weight produces impressive speed.
This train doesn't have an engine on board, nor does it carry any fuel. Instead, we have a pumping station like this one. The pumping station provides either a vacuum in front of the train to pull it, or a pressure behind to push it. And that is where our force comes from.
And since all of our pumping systems are stationary, we can use a large variety of fuels. In fact, we think that there would even be a possibility of mounting solar panels along the edges of the tracks.
In full-scale production, Max and Eric believe the elevated Vector could propel up to 800 passengers to speeds in excess of 290 kilometers per hour. And because the train doesn't rely on traction, as with Brunel's creation, it appears to be an effective solution for climbing hills.
The advantage of the atmospheric rail is it eliminates the dependence of steel-on-steel friction. Consequently, we can go up or down grades that are steeper than traditional rails can handle.
All in all, this pioneering innovation is reviving a forgotten technology from the past, one that could help shape the future of the railways.
I just hope it happens in my lifetime, but if it doesn't, the people are a lot younger. I think they'll be able to pull it off.
This is the future of rail.
Railways are picking up speed, with record-breaking trains pushing innovation to the brink and beyond. But with great speed comes even greater problems, requiring inspired engineering solutions. Japan, a land of islands and mountainous terrain. Building an effective transport network across this spectacular landscape has historically been a problem, and travelling across country extremely slow. In 1940, Japanese engineers set themselves the seemingly impossible challenge of creating a high-speed rail network. And finally, in 1964, they introduced the bullet train.
The influence of the Tokaido Shinkansen is very big to the Japanese society.
The bullet train, or Shinkansen as it's known in Japan, was the world's first high-speed train. This powerful, streamlined machine could travel an unprecedented 210 kilometers an hour, and the country was transformed. Dr. Eiji Nakatsu was General Manager of the Technical Development Department.
In 1964, after the opening of the Tokaido Shinkansen, we could have so many passengers, tourism, and business trips. The airline between Tokyo and Osaka was demolished, and the motorways utilization was also temporarily decreased.
The 515-kilometer journey between Tokyo and Osaka in the Tokaido Shinkansen was now possible in just 4 hours, as opposed to the previous 6.5 hours. But it wouldn't take long before Japan wanted to go even faster.
The first, of the beginning of the Tokaido Shinkansen, the maximum speed 210 km per hour. After that, we have tried to realize the speed up to 120 km per hour or 270 km per hour.
But increasing the speed of these super trains created an unexpected phenomenon.
When our train goes rush into the tunnel with high speed, the shock wave stand up and go to the exit of the tunnel. And on the exit, we can get a big bang, down like that. And also, this pressure wave spread in all directions.
Like a piston in a cylinder, as the train sped into a tunnel, it generated atmospheric pressure waves, forcing the air out of the tunnel exit at the speed of sound, creating what's known as tunnel boom.
For the people on the line, these noises became a big problem because from 6 o'clock in the morning, early morning until the midnight, they were suffered from these noises.
Homes as far away as 400 meters were affected by the ceaseless noise. And if trains were to go faster, it would only get worse. So how do you keep up with the demand for more speed and at the same time reduce the noise pollution? The answer came in the form of the newly designed 500 series. Designed by Dr. Nakatsu, he created a revolutionary new shape inspired by nature.
I am a bird watcher. My hobby is bird watching. Kingfisher jump into water to catch game from the air with lower resistance and into water with higher resistance. This is very similar to the train set rush into tunnel. That gave me a good idea.
A kingfisher dives into the water at high speed. And even though water is 800 times denser than air, it barely makes a splash. The kingfisher's streamlined success lies with the shape of its bill.
I realized that kingfisher could be a good inspiration for our head shape of the Shinkansen trains.
The new 15-meter nose cone almost exactly replicated the bird's bill shape, producing remarkable results. Introduced in 1997, these new super trains had 30% less air pressure resistance and could reach the record-breaking speed of 300 kilometers per hour. And the tunnel boom was dramatically reduced. It was a major breakthrough in fast train engineering, setting a template for the future.
This project was not made by myself. So many staffs or the personals worked together for this project. And I am proud of it. And this train set 500 series gave a good influence not only Japan but also all over the world.
The bullet train is an undisputed high-speed icon. Since 1964, it's been refined several times over, getting quicker each time. But the latest bullet train engineers have turned their attention to the fastest technology of all, maglev. Still in its trial phase, the new magnetic levitating bullet train has surpassed 600 kilometers an hour. This frictionless train hovers above the guideway and relies upon the properties of superconductors for its extreme performance. Physicist Andrew Steele explains.
A superconductor like this one is a material that has no electrical resistance when it's cooled below a certain critical temperature. So when we get this down to minus 200 degrees, it's going to conduct electricity but without losing any energy. So if I drop it into nitrogen, that's cooling it down to that incredibly low temperature. When you bring it near to the magnets, it sets up an electrical current inside the superconductor, which keeps it levitating there. But that electrical current is stopped as soon as the superconductor gets above that critical temperature.
But if the superconductor remains cold in its superconductive state, the current will continue to flow almost indefinitely, creating an intense magnetic field.
We can use a principle very similar to this to try and make an example of a frictionless transport system. Here we've got some liquid nitrogen again. We just pour the nitrogen onto the superconductor. And because the superconductor is being cooled down really close to those strong magnets, it memorizes the magnetic field that it's cooled down near. And that means that it wants to stay in the same position relative to those magnets. So since the magnetism is the same all the way around the track, that means that it'll be stuck to this particular path. If I give it a little push, it'll go around and around for a very long time. So you can see that this kind of electromagnetic levitation with superconductors allows us to create a friction-free transport system.
And it's this friction-free technology that allows the Japanese maglev to break records. On board, superconductive magnets cooled with liquid helium to minus 269 degrees Celsius are used to both levitate and propel the train. It's hoped service will begin in 2027, with eventual travel time between Tokyo and Osaka just over an hour. A far cry from the 6.5-hour rail journey of the past, once more securing Shinkansen's status as fastest in the world.
I think the Shinkansen are the most iconic railways on the history of the railways.
One thing has always been a key driving force in the development of railways: the pursuit of speed. While engineers have tried everything, from slick design to slice through the atmosphere, to good old-fashioned brute force, or even tearing up the rule books altogether. In order to create a truly 21st century speed machine, no single stone can be left unturned. Italy. While this country might be renowned for its age-old landscape and for its ancient history, it cannot afford to live in the past. But its drive to be a thriving modern nation faces a seemingly impossible geographic challenge. Italy's 4 largest cities of Turin, Milan, Rome and Naples are spread out across the length of the country, making travel arduous. The only solution to keep commerce flowing: speed. Italy is the home of Europe's newest and fastest train.
We're standing in front of the Frecciarossa Mille, which is the high-tech gem of Trenitalia rolling stocks. You can reach maximum speed of 350 kilometers per hour.
The Frecciarossa Mille, or Red Arrow 1000, is the latest and most state-of-the-art addition to Italy's high-speed electric train network.
You know, Italian high-speed changed way of life in many ways. People, they used to travel overnight or spend the night in the town. They don't have to do it anymore because they can travel during the day thanks to the real journey time between Rome and Milan or Naples.
But how do you create an electric train that is capable of running 350 kilometers an hour and cutting the 579-kilometer journey from Milan to Rome to just 2 hours and 20 minutes? The answer, it seems, is to innovate everywhere.
You know, when you raise speed, you cannot single out one item that makes you go faster. So every subsystem of the train had to be thought again, like the traction system, the braking system, communication, suspension. Like every single piece of the train is affected by the way that we want to run at higher speed.
At the Fleet's depot in Naples, engineer Sabato Citro is getting hands-on with one of these super trains to reveal the secrets behind its explosive speed.
For mechanical components, at 300 kilometers, stress is very high, both if the train is going on straight track or is bending on the track. So that's why we have safety checks here. We have special equipments to make sure that everything is performing at 100%.
Traveling at record-breaking speeds requires a radical rethink. Most traditional trains consist of a single locomotive that tows a string of free-rolling carriages behind it. That means all the power is on one spot. Fine for a slow train, not so fine if you're in a hurry. The Frecciarossa Mille completely breaks with tradition.
When you have a train very powerful and very light, you need a special balance between grip and power. At 300 kilometers per hour, the friction between the wheel and the track is very important.
This remarkable train does away with the usual locomotive altogether.
Normally, a traditional train would be powered by a locomotive, which is a special coach, inaccessible to passengers, with all the system, high voltage system and traction system. While here, using 16 engines, we are using the grip of 16 wheels. This engine has a power of 600 kilowatts, which added to the other motors of the train gives a power of 10 megawatts, which is also compared as 100 cars.
Having electric motors spread along the length of the train means more even and efficient traction. It also means that, instead of a giant powerhouse at the front of the train, there is now just the driver in his high-tech cab.
If you have a loco, you just carry one person, the driver. In this train, we don't have a loco. All the equipments and subsystems are distributed along the train, so we can provide, at the same length, more people on board.
But carrying all those people in comfort at up to 350 kilometers per hour throws up even more challenges.
One of the great advantages of train compared to airplane is that when you travel, you can work. So when we race speed, one of the biggest effort we have to make is to keep the comfort as was in the past. If we don't provide a good subtraction system, it would be like going on a roller coaster. You have very high speed, but no comfort at all.
An uncomfortable passenger ride is usually down to one of, or a combination of, three things. Bumps and vibrations transferred from the wheels to the bogie. Bumps and vibrations transferred from the bogie to the passenger carriage that sits on it. And centrifugal force when a fast train is cornering. The solution for the speedy red arrow lies below the passenger's feet.
This is the bogie of the Frecciarossa 1000. It's connected at this point here to the coach. As you can see here, we have a primary suspension with two springs suspension, which are almost the same used in the car. Here we have the secondary suspension, which is basically an air ball, so it's filled by high pressure air. And this one is very important because it absorbs all the energy, all the vibration in between the bogie and the coach. So this one is essentially the most important one for the passenger comfort. If the train takes a bend on the left, the centrifugal force will push the train and passengers on the right. So controlling the air pressure in these airbags, the train can lean on the left side, and that compensates the centrifugal force without slowing down. This one is the ALS system, the active lateral suspension that works like an arm and keeps the center of the coach in the center of the track. At 300 kilometers per hour, the vibrations are very high, so all the suspensions work together to absorb all the vibration and to make sure that the comfort passengers on board is at the top level.
The multi-layered suspension system makes regular adjustments as the train hurtles between Italian cities.
You don't feel the speed. When you check from the screen, say you're going 300 kilometers per hour, you say, no, it can't be. It's as if you're standing, as if the train is still. You don't feel the speed.
Every aspect of the train from top to bottom has been interrogated and designed for optimum speed. The electrical systems are cutting edge. The joins between the carriages have been covered with aerodynamic rubber, and the entire train has been constructed in the lightest way possible. But all these speedy solutions can create the potential for a dramatic and unwanted side effect. When travelling super fast, a train's cab shape is key. A refined nose may look the part, but if the wind's blowing from the wrong direction, even this can be prone to lift. If the engineers of the super-fast Frecciarossa don't get its front right, the train simply won't stay on the track.
So the special profile designed for this train make the aerodynamic resistance very low at 300 kilometers per hour. The airflow is going on the top of the train, and then here, as you can see, the flow goes under the bogie, thanks to this part here of the profile.
Likened to the neck of a king cobra, this unique flared shape crucially reduces aerodynamic resistance, as well as improving stability, allowing and contributing to the incredible speeds, the full appreciation of which is usually reserved for the driver, positioned in the Cobra's head.
For me, that I'm not a driver, it's always, very amazing to be in the cab. Lets you feel speed, seeing all these posts coming at you very, very fast. The aerodynamic of this train is unprecedented in other projects because this train was designed, built and tested to run at 350 kilometers per hour. So aerodynamics was one of the key factors in building it.
Today, the designers and engineers of the Red Arrow are achieving the impossible.
Thanks to the high-speed trains, we had the chance to change the way of living here in Italy. People can afford to live in Naples and work in Rome. People can afford to live in Turin and work in Milan and vice versa. It's all thanks to the high-speed trains. It's 12 years I've been working as a conductor, and I've worked on a lot of trains. Once we had this train, it changed our way of working.
This is one of the most impressive trains in Europe. I'm very proud of being involved in this project.
Seeing it on the tracks and running at such speed, it's a great feeling.
Since the first trains took to the rails, engineers have been driven by the need for speed.
For the A4s, they're built to be faster and more powerful. They are the ultimate express passenger locomotive design.
Striving for this speed, they've produced extraordinary innovations.
We thought of having a train that was a breakthrough in railway technology, and now we have it on tracks. So it's really important sometimes in life to make a step forward, not to follow technology, but to set a way.
Breaking records across the globe.
The 500 Shinkansen threads also could be the most epoch-making rolling stock in the railway rolling stock's history.
And they continue to push the boundaries to create more impossible railways.